in Santander. Let's start the last day of the workshop. This afternoon is dedicated to dark matter and cosmology. And as I said, the last hour, so the last 15 minutes will be a round table of world-known experts. But now we start with Caitlin Schultz from McGill, and she will give us the overview about cosmological probes and dark matter. Caitlin, please.
All right, thanks so much for the introduction and for inviting me to give this overview talk of cosmological probes of dark matter. It's a real pleasure. And initially, when I had agreed to come to this conference, I was so excited to come and visit Santander. It's a real shame that it's not possible for me right now because of complications of international travel restrictions, but I really look forward to the possibility of one day being able to visit in the future. So without further ado, I will go ahead and talk about cosmological probes of dark matter. This is an incredibly rich and very broad subject, so I'm not going to have really much of a chance to do it justice in just 45 minutes, but I'm going to try my very best and try to cover a lot of different really exciting aspects. Okay. So first of all, I want to make sure that we're all on the same page about this statement that dark matter exists. And we think that to very good approximation, it is dark, so not interacting very much with light. However, there's an asterisk on this statement because of course, from a purely observational standpoint, this is something that we can only ever place a bound on from above. So we can never exclude the possibility that the dark matter has, an infinitesimally small coupling to photons. But as far as what we can tell, what's consistent with observation, this statement is true. And I just want to review some of the, in my opinion, best pieces of cosmological evidence for this statement. So first of all, Big Bang nucleosynthesis, or BBN, tells us quite precisely how much ordinary matter there is relative to radiation, the so-called photon to baryon ratio. And this is really sensitive to this number because if you change the amount of ordinary matter relative to photons, that changes this whole complicated flowchart of different nuclear interactions that's taking place in the early universe. And if you change this, this whole delicate flowchart, you end up really changing the abundances of various chemical elements that we get in the early universe. And so we know the photon to baryon ratio, but we have other ways in cosmology of measuring the total matter density or the ratio of matter to radiation. And we know that that baryons cannot be all of the matter from this measurement. Moving on to the CMB as well as CMB lensing. When we look at this primordial plasma, the afterglow of the Big Bang, we see evidence for essentially what I would consider to be sound waves in this plasma, which are being sourced by both gravity as well as radiation pressure. And in these sound waves, we see evidence for a component of matter which does not appear to be responding to the radiation pressure. And this component of matter, this dark matter, is having a gravitational effect on the visible matter that we can see, the baryons, because it's loading down those baryons and it's tipping the scales between gravity and radiation pressure more towards gravity. Okay, this is also reflected in large-scale structure. So because in the very early universe, prior to recombination, we have this component of matter which doesn't feel radiation pressure very well, that stuff, that dark matter, is able to essentially get a head start on structure formation, and it's not going to be impeded by this radiation pressure to get going on starting to collapse. And so these clumps of dark matter end up becoming the seeds of structure formation that the baryons later fall into. And you need these seeds of structure formation in order to explain the cosmic web and other aspects of large scale structure. Finally, on much, much, much smaller scales, we have evidence of dwarf galaxies locally in the neighborhood surrounding the Milky Way, where dynamical studies indicate that dark matter makes up the vast majority of the mass in these systems. So for example, here's a picture of a dwarf galaxy. We also have ones like Segway 2, which are extremely dark matter dominated and light. So in combination, all of these different cosmological probes tell us the total amount of matter and the total amount of ordinary baryonic matter, and crucially, these are not equal to each other. Tells us the ratio of the dark matter and baryon densities. So that's something you can get from looking at the odd peaks of the CMB, for example. It tells you that dark matter plays an incredibly important role in seeding structure formation, so getting the whole process of structure formation going in the very early universe. And the dark matter must be long-lived enough to still be important for gravitationally binding structure at the present day in dwarf galaxies in our backyard. And in my mind, this is kind of the definitive list of things that we positively know about dark matter, things that we can say with relative certainty. And this has been the status quo for the last several decades. So, but naturally we want to know, what is this dark matter? What is it made of? How is it behaving? How does it fit in with the rest of the standard model that we know and love? And from a cosmological point of view and a rather empirical point of view as well, I would say that we're still quite in the dark on this question. And one way I will just try to highlight the sort of, in my mind, relative ignorance on this question is by focusing on one parameter, which could describe the dark matter, namely its mass. And so here I'm showing a wide range of different possibilities for the dark matter mass, which I have shaded according to different qualitative behavior of the dark matter in these different shaded regions. And what you'll note is that there are many possibilities and that the end caps actually are, giving you just qualitatively different behavior. So on the very high mass end, you have a scenario where dark matter is not made of particles, but rather it's made of compact objects, like, for example, primordial black holes. There are cosmological constraints on this side of the mass range, coming from things like not messing up the CMB or not messing up structure formation in very, very low mass dark matter dominated systems. Moving down, you start getting into the particle dark matter candidates like the composite dark matter, WIMPs and light dark sectors, and sterile neutrinos that I think we've heard a lot about for the past several days, as well as going down to the very low mass end, you get into a regime where the dark matter is better described on macroscopic scales as behaving like a wave, a classical wave with a high occupation number. This includes dark matter candidates like the classic QCD axion, but going down even to much, much lower masses, we have situations where the de Broglie wavelength of this dark matter can be comparable to the physical length scale that corresponds to dwarf galaxies. And so that's where you can get a bunch of constraints on that end as well. So we have roughly 90 orders of magnitude to play with in mass, and that's just one parameter that could be describing dark matter. We also want to understand, how is it coupling? How is it interacting? Is it talking to us? How does it fit in with the standard model? And that's a whole different axis of parameter space. And just to very schematically highlight that, here's kind of a schematic depiction of how I like to think about the standard model. I've taken all of the particles and I've coordinated them into this Venn diagram according to which forces these particles feel. And the amazing fact that gravity sits at the outermost regions of this Venn diagram is an amazing fact. So the fact that gravity appears to be universal is what has allowed us to discover the presence of this new component of matter, this dark matter. So given that we want to understand how this dark matter is behaving, we could be in a situation where, for example, maybe this dark matter has some direct coupling to the standard model. For example, if you have something like a dark sector, perhaps there's a new force which has some sort of coupling to particles in the standard model, or maybe it's an indirect coupling to particles in the standard model. Maybe there's a whole rich dark sector, so it's not just the dark matter and the new force, but there might be other auxiliary states in the spectrum. And if this is the scenario that the universe has provided to us, then many of the traditional ways of searching for dark matter that have been discussed over the past several days will be relevant. So the sort of make it, shake it, break it paradigm of looking for dark matter in direct detection, indirect detection, and accelerators will be very helpful here. However, the universe might not be super kind to us. We might be in a situation where this sort of new sector that the dark matter lives in, it might be decoupled from the standard model. There may be no direct couplings, and in that case, we have to rely on gravity alone. So again, the fact that gravity is universal is super helpful, even though it's super weak force. Obviously, it can still help us to learn what's going on inside of this dark sector. And in fact, even in cases where there is a direct portal coupling between the dark matter and the standard model, as we'll see throughout this talk, sometimes gravity is still the most helpful in determining what are the properties or what are the constraints on this kind of sector. But the point being is that theories of dark matter are incredibly diverse. And so clearly multiple approaches and different kinds of systems are going to be needed to probe, all these different properties, different qualitative kinds of dark matter particles, different qualitative kinds of interactions and couplings. And I think cosmology and astrophysics provide the perfect playground or perfect sandbox for this, where we have all of these different kinds of astrophysical systems operating at different length scales, time scales, and ambient environments. Oh, sorry, someone drawing on my slide. Was there a question or? Okay, I'm gonna move on. So multiple systems are needed, and cosmology can provide that. So for the remainder of my talk, I'm gonna be focusing on gravitational signatures of the dark matter thermal history. I'll clarify what I mean by that shortly. I'm going to focus on gravitational signatures of the possibility that there is a component of dark matter that has an ultralight mass. And I'm going to be focusing on the dark matter interaction cross-section with baryons. So this is an example where there is a direct coupling between dark matter and baryons, but gravity is still actually the best way of searching for that coupling. And in the context of these different types of dark matter behavior or different signatures, I'm going to discuss some recent dark matter interpretations of observables, including BBN, the CMB, 21 centimeter cosmology, the Lyman alpha forest, strong lensing, and probes of near-field cosmology with local subhalos. So it's going to be a lightning overview of a lot of these topics. I'm not going to be able to go into very much depth, but please feel free to ask questions in the Q&A later on if you want to know more. Okay, so really briefly, let me just get into the signatures that I want to talk about. So first one is the thermal history. And there's a couple of things that I mean, or that are related to this quality of dark matter of having a thermal history. One sort of aspect of this is that dark matter could be in contact with the standard model plasma in the early universe. And so this is the same sort of make it, shake it, break it diagram that you see in the context of direct, indirect, and collider searches for dark matter in the lab. And these are the same kinds of processes, except in this case, the standard model material that this is happening off of is the standard model plasma in the early universe. So different properties than what we might have in the lab, but you can still learn really interesting things. In particular, if dark matter, for example, if you have a theory where dark matter starts out in its own sector as a separate thing that's thermalized and secluded, if it then later thermalizes, whether kinetically or chemically with the standard model, then that's going to actually have an effect on its thermal history. And as we'll see, it's going to affect a bunch of different kinds of observables. And entropy can also transfer between these sectors, which can change the evolution of the universe. Additionally, dark matter might be born through either thermal or non-thermal processes. So for example, with classic dark matter freeze out, we have dark matter that's thermal and then it's depleted. Its number density is depleted over time through annihilations. But there are other kinds of ways of making dark matter where the time arrow is reversed, and maybe you're making dark matter through a process from the standard model. So there's a lot of different ways of tweaking the dark matter thermal history through these kinds of interactions. There's another thing that people typically mean when they refer to a dark matter thermal history, and that's this scenario where you have dark matter that decouples while relativistic. This is the so-called warm dark matter scenario, and it has these initial conditions where the dark matter abundance is determined by this relationship between the dark matter's mass and its temperature relative to the standard model. This kind of initial condition situation was inspired by neutrino decoupling, and this formula will apply for any particle that decouples while it's relativistic. And here, the temperature ratio T chi over T gamma is determined by entropy considerations. So in particular, if you have a lot of degrees of freedom in the bath when this process decouples, then those degrees of freedom can then preferentially heat up the photons and not this other decoupled thing. And so that's going to change the temperature ratios. One thing I want to note, which I feel like is not often mentioned in the literature, is that these days, as we'll see, people are constraining KeV scale warm dark matter. But to satisfy these initial conditions for the KeV scale, you need the temperature ratio between the dark matter and the photons to be large enough such that you have roughly between 1,000 and 10,000 extra degrees of freedom lying around to dilute and give you that temperature ratio. So this kind of scenario, I think, is a very useful sort of toy model or benchmark because it's been so well studied in the literature. But it's probably not such a good idea to take this too seriously as a literal model of what's happening in the early universe, because then you have to explain where, you know, several thousand degrees of freedom are coming from. But like I said, this model still has its utility because it's very well studied and it has some very direct analogs, for example, to sterile neutrinos. So the effects of this latter scenario, of this decoupling while relativistic, are that basically you have an effect on structure formation because, again, you have these initial conditions where you have this inverse relationship between the mass and temperature of the dark matter. So the lighter you make the mass, the more you have to raise its temperature. And when you have a low mass, very hot thing, that means its typical velocity is going to be big. And if it's bigger than the typical escape velocity of nascent halos that are trying to collapse and form, then you're going to erase those halos because the dark matter is not going to be gravitationally captured inside of there. And so here are two simulations showing what I mean explicitly. So in the right panel, you see that you have a lighter, hotter candidate for warm dark matter. And you see that what that's done is it's basically blurred out and fuzzed out this image. So that's the smoking gun signature that you can look for in this context. Okay, so that's one kind of signature that I want to talk about in this talk. Another kind of situation is the situation where you have ultralight dark matter, where for ultralight dark matter, you actually can exhibit wave behavior on macroscopic scales. Since the de Broglie wavelength of dark matter scales like 1 over the mass, if you crank down the mass and make it super tiny, like I'm talking on the order of 10 to the minus 22 eV, then that de Broglie wavelength ends up being roughly the size of dwarf galaxies. And so here in this panel, I'm showing some simulations by Philip Mox and others showing the same realizations of the same initial conditions, but in one scenario having particle dark matter and in the other scenario having this kind of wave-like behavior of dark matter. And you can see that there are a few notable differences between the two. For example, these subhalos that I've circled over here don't have a clear analog in the wave dark matter picture. And so we can see that this wave behavior seems to be erasing structure below a certain scale. And the interpretation for why that is that it's related to the uncertainty principle, because you can't pack things together and also have them localized in velocity space at the same time. And that is what you would actually require in order to have a gravitationally bound dwarf galaxy. So you're erasing structure. At the same time, you're introducing all of this very fine sort of interference fringes over here coming from different waves of dark matter stochastically interfering with one another. So this kind of behavior, which is manifest on the scale of dwarf galaxies, can also affect structure formation. So here what I'm showing is the transfer function for a variety of different axion or ultralight dark matter masses in the ballpark of 10 to the minus 21 eV. And you can see that this T of K, this is the ratio of the power spectra to the cold dark matter scenario, and you see suppressed structure on small scales, again, because of this wave behavior coming from the uncertainty principle. If you want to actually do science with this on subgalactic scales, you have to take into account a bunch of additional things, like modified excursion set critical collapse barrier, and you have to think about, tidal stripping and all these effects. But these are things that we can actually do all of these things and try to model them. Lastly, I mentioned dark matter interactions with baryons prior to recombination. I already touched on that a little bit when I mentioned the thermal history, but I want to talk about a slightly different scenario, one in which the dark matter does interact a little bit with baryons, but not enough to necessarily thermalize with those baryons. So the picture of what's happening here is, again, when you have your pre-recombination photon baryon fluid, It's trying to gravitationally cluster together because you have some seed perturbations which were laid down in the early universe from a theory like inflation or some alternative to inflation. And then things want to cluster. The collisionless dark matter is able to cluster. It sinks to the bottom of the gravitational potential well. The photon baryon fluid also tries to cluster, but radiation pressure becomes quite insurmountable. And so you get these acoustic oscillations. And you're able to see the effects of the dark matter on these acoustic oscillations because the dark matter is weighing down, or it's loading down these baryons and changing the shape of the gravitational potential that these things are oscillating in. And so that's a great piece of evidence for dark matter in the collisionless case. But suppose you're in a scenario where every once in a while, the dark matter has an interaction with this photon baryon fluid. So if that happens every once in a while, the photon baryon fluid can actually drag some of this dark matter out from the depths of this potential and kick it out. And it can actually affect the subsequent evolution of these oscillations, because then what you've done is you've taken some of the material out of the deepest parts of the potential. You actually, is there a question?
I will mute everybody. No worries. Okay. Go ahead, please.
Right. So there's So you've dragged some material out of the gravitational potential and you've made it shallower than it would have been otherwise if you had collisionless dark matter. And so this is going to affect not only things like the CMB, which is the most obvious because this is happening right around the time of recombination, but it can also affect later structure formation because you're taking these potentials that would have been much deeper and which would have been the seeds of structure formation, and you're taking those initial conditions and you're fuzzing them out essentially. So you're smearing out the matter more than it would have been otherwise. This was something that was, I think, first pointed out in a 2013 paper, but this has really come into maturity as a really interesting probe of dark matter. Okay, so having sort of laid the foundations of what kinds of effects I want to look for, I'm now going to go through a lightning fast rundown of a bunch of different kinds of cosmological probes in this context, starting with BBN. So BBN, I think most people can appreciate, is a way of testing things interacting with various atomic nuclei, right? Because that's BBN is this set of nuclear reactions that are building up and giving you an abundance of light elements in the early universe. But I think one thing that's not always appreciated is that BBN is also a gravitational measurement. In particular, so BBN, all of these rates and the times at which they freeze out relative to one another, all of those things are very sensitive to the Hubble expansion rate in the early universe, because if these various rates can't keep up with the Hubble rate, that's telling you that as the universe is expanding, it's becoming harder and harder for these particles to actually find each other to undergo various processes. And since the Hubble expansion rate is gravitationally dependent on the ambient density of the universe, BBN is therefore sensitive to what's happening gravitationally in the early universe. At this epoch of the universe's evolution, the universe was radiation dominated. And so we often parameterize changes to the Hubble expansion rate in terms of this N effective term, which tells you about modifications to the radiation density. In the standard model, N effective is a little bit bigger than 3. It's around 3, but it's a little bigger for reasons that are a bit technical. But given that we can measure these elemental abundances and we can constrain N effective from BBN as well as from the CMB for similar reasons, we can actually constrain the possibility of having extra relativistic degrees of freedom that would contribute to the radiation density in the early universe. And here's actually a really recent example. This paper came out on the archive last week, I believe. And this is showing what would happen if you have vector portal dark matter. So dark matter coupling to some heavy A prime, which then kinetically mixes to the standard model photon. And what these authors found is that anything lighter than a few MeV, depending on the spin statistics of the particle, is actually excluded, all the way down to cross sections of 10 to the minus 46 centimeters squared. And above that cross section, these particles will have thermalized in the early universe. And because of their light mass and because of the temperature of the universe at that time, they will therefore be relativistic and they will be gravitating just like radiation would. And so therefore they're going to contribute to N effective. So you get this super strong constraint on these particles down to, from few MeV and down to arbitrarily low masses and down to arbitrarily low, well, not arbitrarily low, but down to very, very low, 10 to the minus 46 centimeters squared cross sections. And so this is a very, very powerful gravitational probe of a situation where you do have this direct coupling to the standard model, but it's really gravity is telling you that there's, something would be amiss if this were to be how our universe worked. Next, I want to focus on the CMB very briefly. And again, this time I'm going to focus on this dark matter baryon drag, which would be apparent and which would affect these acoustic oscillations in the early universe. And I actually want to hone in a little bit on a particular kind of scenario. So if you have dark matter baryon drag, the CMB is especially good at constraining scattering via a light mediator. Because if you have a light mediator in the problem, the cross section for interaction between your photons your baryons and your dark matter is going to scale like velocity to the -4. And what that's telling you is that as the universe is expanding and all of the velocities are redshifting and they're being Hubble damped, the velocities are going down, typical velocities are going down, which means that for velocity to the -4 scattering, your drag rate, which is what's plotted here, is going to start to go up. So this is the drag rate in units of the Hubble rate. You can see for the n equals -4 case, which is the v to the -4 scattering, you get a ton of this drag effect happening right around the time the redshift of recombination. And so the CMB is going to be very sensitive to this type of scenario. I want to briefly talk about a specific realization of this type of scenario, which is dark matter freeze-in. This is a scenario where you're making dark matter from extremely rare, extremely sub-Hubble processes in the early universe. So, you have some tiny branching ratio where once in a while, some process in the thermal plasma will make dark matter, and that dark matter is so weakly coupled that it will never talk to anyone again. And so this is a really interesting sort of scenario. Freeze-in sort of represents the smallest possible coupling that you can have between the dark matter and the visible sector, where the dark matter has any meaningful degree of contact with the standard model. So in some sense, it's a little bit of a final frontier. And when I say a small coupling, I mean like Q of 10 to the -11, so alpha of order 10 to the -22 or something like that. One thing that I think is also not always appreciated about this kind of mechanism is that it's the simplest way of making a lot of kinds of dark matter, including charged dark matter, or dark matter that has some effective coupling to standard model photons. You hear a lot of references to charged dark matter these days, but people will often treat it very phenomenologically without making any reference to where it comes from. And actually, if you have couplings above the freeze-in coupling and below the freeze-out coupling, which is excluded, then you're going to end up with an overabundance of dark matter, which you need to explain in your model. So this is freeze-in. It's a fairly interesting model. Like I said, it's a final frontier. It's also a key benchmark for direct detection experiments, particularly below the MeV mass scale. Some proposed direct detection experiments sitting here, which I'm not going to have time to go into, but there's really broad interest in constraining this type of model. And so using the same arguments that I was just saying about low velocity enhanced scattering between particles, between dark matter and particles in the primordial plasma, you can apply the same rationale. So here what I'm showing is a plot of the change in the primary CMB, the delta CLs, that you would get if you had the couplings that are relevant for freeze-in. And here I'm showing a bunch of different thermal histories, so different phase space distributions. You can see here that the phase space does matter, and that's because it's a velocity to the -4 scattering, so you're very sensitive to what is the exact thermal history of this particle. But the upshot of this is that with Planck 2018 data, cross sections that are greater than 10 to the -41 centimeters squared are ruled out for cold dark matter with this behavior. And freeze-in dark matter is excluded below 20 keV, again, in spite of the super, super weak couplings that you see. So that's very powerful. I'm going to now move on to some kind of more exciting upcoming probes, like 21 centimeter cosmology. So in 21 centimeter cosmology, we're sensitive to this kind of behavior from clustering and from the thermal history, particularly around the time of cosmic dawn, because if you think about the 21 centimeter signal, most of the time you're seeing it in absorption because these 21 centimeter atoms are being backlit by the CMB. And right around the time when the first galaxies are forming, the CMB photons have a very similar effective temperature as the so-called spin temperature of the gas, the 21 centimeter states. And so you don't see very much of a signal, but at some point when the first galaxies form, the photons from those first galaxies is going to couple the spin temperature to the kinetic gas temperature through something called the Woodhuizen field effect. And so you're going to start to see a pretty big dip. You're going to see absorption of your 21 centimeter line. But at some point, those same first galaxies, which created this coupling and which drove the spin temperature down, those same photons are going to heat up the gas. And so the kinetic gas temperature is going to go up and the spin temperature will follow. And so what you end up with is this characteristic trough right around the time when the first galaxies are forming. Now, in order to form the first galaxies in a bottom-up picture of structure formation, you need to start with the smallest halos. And like I mentioned before, those smallest halos are very susceptible. They're very fragile to changes to the thermal history where dark matter might be zipping around, suppressing their formation. So, for example, if you have warm dark matter, what you're going to see, and first of all, I apologize, the axis is flipped, so now high redshifts are on the right-hand side. But what you're going to see if you have warm dark matter is that the onset of this trough is delayed relative to the cold dark matter case. And the trough is also much thinner than the cold dark matter case because structure formation, if it's bottom up, once you start getting to these larger halos, you actually catch up with CDM, so it's thinner. You can also look not only in the global signal, so the monopole signal, but you can look at perturbations as well to try to look for the same kind of effect, but it's much more subtle in terms of perturbations. But when you think through very carefully how to do that, what you find is that you have the same sensitivity to early structure formation and how it would affect the first kinds of halos, which would be hosting the first galaxies and the first stars. And so what these authors found is that with Hera, which is, I think currently actually just had its first big data release, and it's still partially built, but taking data. So with Hera, you will be able to probe all the way up to 14 keV warm dark matter, or you'll be able to probe all the way up to 5 × 10⁻20 eV fuzzy dark matter. And both of those are through the effects of suppressed structure formation on small scales. Okay. Next, we have the Lyman alpha forest. So that's a very well-studied probe of small scales. Just to give a cartoon of how this works, we have some broadband spectrum from some high redshift quasar. The light from that quasar is traveling to our telescopes, but it's passing through regions, little clouds of neutral hydrogen. And each time it passes through one of these clouds, you're going to get an absorption feature corresponding to the Lyman alpha transition. But the whole spectrum is moving to the right as the universe is expanding and redshifting. And so by the time this light reaches our telescopes, we end up with the envelope of this broadband spectrum with many spectral lines, a dense forest of spectral lines, you could say, each telling you where the location was along the line of sight, what was the redshift along the line of sight, where you had some little cloud of gas. So this is a well-established way of trying to constrain things like warm dark matter through, again, its effect on suppression of clustering on small scales. The current best constraints are in the ballpark of 3 to 5 keV, depending on specifics of how various people are modeling the IGM. But recently there have been some developments. So a paper last summer by Keir Rogers and Hiranya Paris showed that if you have both improved spectral resolution from better spectrometers, as well as more robust ways of doing simulations and really simulating all of the various possibilities for the IGM, and then emulating, so using machine learning to interpolate between these possibilities and these simulations in a principled way, using this combination of techniques, you can really extend existing limits, and you can actually constrain with current data fuzzy dark matter up to masses of around 5 times 10 to the minus 20 eV. So a super strong constraint on fuzzy dark matter. Next, I want to describe some updates with regard to strong lensing. So with strong lensing, you can probe substructure. For example, if you have some very bright background quasar that's gravitationally lensed by a foreground galaxy, it can appear as 4 images. This is called quads. So there's 4 images, and the locations and relative fluxes of these images can be quite sensitive to the substructure in the lens galaxy. In particular, the locations and relative brightness of these images corresponds to some very non-trivial combination of various second derivatives of the lensing potential. So you're very sensitive to small scale structure that way. And just to show one example, here is a realization of an effective convergence map for one example of one of these quads. And here you can see that in this realization, you have tons and tons of substructure. Here I've circled this scale. This is the half mass or half mode scale of 10 to the 7.4 solar masses. So you have evidence roughly in that neighborhood that you need to have subhalos. So if you translate that into a constraint on dark matter, an analysis of 8 of these quads led by Daniel Gilman in 2019 excludes warm dark matter lighter than 5.2 keV. And a different separate group led by Sui et al. Looked at different quads and used a different method for analyzing their data, and they come up with a very similar number. So that's very reassuring. You have independent groups, independent analyses, giving you very similar bounds. With this information, with this fact that you see evidence for these subhalos in these systems, you can then try to bootstrap constraints on other kinds of dark matter properties from this. For example, last year, trying to compare the subhalo mass function that's being inferred by these kinds of observations and comparing that subhalo mass function or that limit on the subhalo mass function to a subhalo mass function that you would get if dark matter were made of fuzzy dark matter. And here you can see that at the level of warm dark matter that they're constraining, where they're looking at 5.2 keV constraints, this is the halo mass function or subhalo mass function that you would get in that theory. It looks very, very similar and is actually even a little bit bigger than the one that you would get from fuzzy dark matter in this mass range. And so if this one is excluded, then this one is likely also to be excluded as well. So you can kind of bootstrap your way using things like warm dark matter as a useful benchmark model and try to make interpretations of other kinds of models. Lastly, I want to talk a little bit about recent developments in finding fainter and fainter dwarf galaxies and using their inferred counts and their properties to learn more about structure formation on very small scales, cosmology. In particular, in recent years, we've been pretty good at actually finding more and more dwarf galaxies over time. Here is actually a plot from Drickler-Wagner et al. Representing the DES Dark Energy Survey collaboration. And you can see shown here are various fields of view of different instruments, including DES as well as pan-stars. And shaded here are all the different dwarf galaxies which were discovered by these different instruments over here. And we can see that we're just doing much better over time, finding more and more. And with all of this rich data, we can try to better sort of calibrate our understanding of the properties of the galaxies that live inside of the dark matter halos that are hosting what we observe. In other words, the galaxy halo connection. So that's what was done in this sort of tour de force paper led by Ethan Nadler. Basically, the idea is if you sort of re-simulate a bunch of different Milky Way-like halos from a large volume under different assumptions about the underlying cosmology, then you take the subhalos in your realization, you paint galaxies on according to some sort of galaxy halo connection type of model, you apply your observational selection functions, and you calculate the likelihood, and then you just rinse and repeat iteratively until you are able to calibrate things like the effects of satellite mass and size and baron effects and tidal stripping, galaxy formation efficiency, and so on and so forth, intrinsic scatter. But once you do all of those things, once you've really trained this model, you can then infer something about the population of dark matter halos, which would be hosting these things. And so with that updated understanding, you can make statements like that the presence of low mass subhalos is consistent with cold dark matter after accounting in particular for things like selection effects, which can be really important, as was first pointed out by Annika Peters' group and Stacy Kim as well. So with that being said, and given their sensitivity and the fact that they're seeing something that seems to be consistent with cold dark matter, they can rule out warm dark matter masses below 6.5 keV. Again, warm dark matter may or may not be the most realistic theory of what's happening in the early universe because of this issue with the number of degrees of freedom required for literal warm dark matter. But again, you can make a lot of really helpful analogies to other theories. So for example, probably the most direct comparison would be to sterile neutrino dark matter. And here what I'm showing is the parameter space for sterile neutrino, the mixing angle versus the mass. And what I'm showing here is the Shih-Fuller mechanism for making this sterile neutrino dark matter. It's a non-thermal mechanism. And what you can see here is that, so previously there were these SDSS constraints, but with the addition of the dark energy survey, halos that were found can exclude nearly the entire allowed window for the Shih-Fuller mechanism to explain dark matter and give you warm dark matter. There's maybe this tiny little shred down here that's left, but really there's not much else that's left. In particular, this point right here corresponds to the sterile neutrino interpretation of 3.5 keV line. So if you believe that the 3.5 keV line is a real line, which I think is perhaps a controversial statement, and if you believe that it has to come from dark matter, then it can't be from this kind of mechanism. It has to be some other mechanism. Okay. You can also bootstrap other non-thermal phase space distributions off of these kinds of constraints. So not only Shih-Fuller, but again, going back to this example of dark matter freeze-in, which can also lead to a non-thermal distribution. And what you're seeing here is the phase space, the primordial phase space from this process, which is creating this highly non-thermal phase space with this very low velocity peak and then a fat tail over here, looking highly non-thermal. But note that I've plotted the momentum of this distribution in units of the photon temperature. So you can see that even though it's born non-thermally, the dark matter is still hot in a sense because it's moving very fast. And this is true for all times because both of these quantities are redshifting at the same rate. So what you can do with some arbitrary distribution is you can try to map warm dark matter constraints onto these other thermal histories. Here I'm showing you the transfer functions results from both class and CAMB Boltzmann solvers for freeze-in. And you'll see that there's a difference between the thermalized case and the non-thermalized case. What that is coming from is the possibility where, if dark matter is able to scatter with itself and self-thermalize, then the dark matter must have a non-trivial speed of sound. Whereas in the case where it doesn't self-thermalize, it's like the dark matter was born, it was shot out of a cannon, and it never talks to anyone again. It's just free streaming, and so it's acting more like neutrinos. So in either of those cases, you can compute what the suppression of the matter power spectrum would look like. In both cases, it looks kind of similar, and you can try to map that onto the warm dark matter transfer function that you would get from the warm dark matter candidate corresponding to DES limits, and you can try to do a mapping that way and estimate limits on freeze-in that anything below 17 keV approximately can be excluded. You can finally do the same thing with dark matter baryon scattering. Like I talked about earlier, if you have dark matter baryon scattering, you make the gravitational potentials more shallow and you disrupt structure formation. And in particular, as always, you disrupt it the most for the smallest scale halos. Those ones are the most delicate. And so this is the transfer function that you would get for a velocity independent scattering. So no velocity dependence to the scattering, showing a bunch of different transfer functions for warm dark matter here, and at the same time showing a bunch of different cross sections for that dark matter baryon interaction. And you can see that they give very similar suppression. And so with the constraints on warm dark matter, you can bootstrap that to constraints on the interaction cross section. And you can see here that there's a nice degree of complementarity for the velocity independent case, you're actually going to do better than the CMB. It's not true for the v to the -4 case, but for the velocity independent case, you can actually beat CMB by a couple of orders of magnitude and really close a bunch of gaps that exist with cosmology as well as other terrestrial experiments. So it's all very complementary to other experiments. Finally, in the future, we're going to be able to potentially look below the threshold of galaxy formation. And I think this is quite exciting. Lots of methods, including things like stellar streams, which have already claimed a limit. We've got other proposals, including lensing, as well as looking at direct kinematics, so looking for stellar wakes and proper accelerations. Thank you. I'm going to wrap up very quickly. So I just talked about a bunch of different probes, but I want to tie them all together in the context of one model. Yet again, here are all of the constraints that I just talked about on one dark matter model. Yep, I'm just going to wrap up. Like I just have one more slide. Okay. And you can see that there's a high degree of complementarity here. These are all independent astrophysical systems. And so you can actually combine these different systems if you're feeling particularly bold. But one thing I want to again emphasize is that this model that I talked about is a direct detection benchmark. So we have cosmology constraints from below, direct detection constraints from above, and that's a beautiful situation to be in. There's a high degree of complementarity. So with that, I will just leave up my conclusion slide. Thanks very much for your attention, and I'll take any questions now.
Thanks a lot, Caitlin. And sorry for the last interruption. This was unintended.
Oh, that's all right.
I was just not muted. Thanks a lot for this great and comprehensive overview.
Thanks.
And yeah, are there questions? Please raise your hands. Well, okay. Konrad, please go ahead.
Yeah, hi. Thank you for this interesting talk. And I think actually I have a lot of questions, but in general, now you showed some that you, for example, can exclude the KEV sterile neutrinos, but all of these cosmological probes put together. So what is your take? So what is most likely now the dark matter particle?
Oh, that's a tough question. Do you have an afternoon? No. My personal opinion is I just like whichever dark matter model I know how to test. I don't tend to have a very strong theoretical prior, so I like to just see, how can we mess up the universe and what would happen. So that's kind of my preference, but that's my personal opinion.
Okay, thank you.
Maybe I can ask something in a similar direction. You were discussing particularly warm and even wave-like dark matter, but you always said, yeah, but this is constrained and here we have that limit or so. So I understand that in principle, there is still room for this kind of dark matter, which is not excluded. From your talk, I would have gotten the impression that it is, via the various experiments, extremely severely constrained already, but maybe I didn't see where it can still exist. Yeah, the lighter it is, you said, the hotter it should also be, and then you don't get the right structures, etc.
Yeah, I mean, I think it depends on what is the benchmark. So if the benchmark is 10 to the minus 22 EV, then and if that's the literal thing, then I think that's probably excluded. I think with any time when you're doing astrophysics or cosmology, right, in any individual system, there's certainly room for systematics to creep in, and that's something that you have to be very, very careful about, or maybe theory uncertainties as well as systematics. But I think at a certain point, when you start stacking all these different kinds of probes that are all making independent assumptions about both what the dark matter is doing, because it's different length scales, as well as different assumptions about the system in question and different analyses, I think at that point it starts to become, okay, maybe we're going to take this pretty seriously. So maybe the literal value of 10 to the minus 22 is ruled out. But I still think, this is still an interesting possibility. 10 to the minus 22 was a number that arose because it could potentially give you a missing satellites problem. But nowadays we know that there really is no missing satellites problem, because if you apply the corrections from the selection function, we sort of found all the satellites. This was pointed out, I guess, in 2017 or 2018 by like Annika Peters' group. So we sort of found the satellites. So we don't need to explain missing satellites anymore. So that kind of original motivation has kind of gone away. But I still think that the underlying theory reasons are interesting, like, some of the string theory inspired notions of why you expect lots of light bosons distributed across a wide range of masses. So I think it's still interesting to consider this possibility and try to learn more.
Okay, thanks. We are already out of time, but maybe one very short question. I can't make out the name. Andrew, maybe?
Hi, yeah, I'm Shashin. It's just my email. One question is, does the EDGES experiment say anything about the nature of the dark matter? I mean,
yes, good question. I think that's a very controversial question, so it may not be the shortest question, but I think—
Short answer, please.
Excuse me?
Short answer, please.
I'll try to give a short answer. I think extraordinary claims require extraordinary evidence. What EDGES saw is not really consistent with what anyone was expecting. And so I think we definitely need some sort of follow-up from another experiment before I'm personally comfortable speculating about what it means for dark matter.
Okay, thanks a lot. I think we have to leave it here. Please stop sharing and we come to our next talk by Matthias. Hi, Matthias. Good to see you again. Yeah, please show your slides. You have 70 minutes and I'll give you a 2-minute warning.
Okay, perfect.
Yeah.
All right, can you see my screen?
Not, yeah, now I can, yeah. Okay, yeah.
Right, I'm just
How
starting.
warm are non-thermal relics? Please, Matthias, go ahead.
Thank you, Sven. Well, first, thanks to all the organizers for giving me the opportunity to talk today. It has been really pleasant. So today we'd like to talk about out of equilibrium dark matter. And we already have a nice review of the cosmological probe of dark matter by Kathleen. So in this talk, I would like to try to answer 2 questions. First, how dark matter is being produced. And secondly, is it possible to actually probe its production mechanism? So in this talk, I will focus essentially on dark matter being produced in out of equilibrium state. And by this, I mean that I consider dark matter as being particles that never achieve thermal equilibrium with itself or the standard model plasma in the universe. So there are various possibilities of producing this kind of out of equilibrium dark matter candidates. Let me just give you a bit of context. So in this usual picture, in this usual inflation picture, inflation is realized while a scalar field is slowly rolling down its potential here. And at some point, this field oscillates around its minimum and starts to produce standard model particles. And so this is the so-called radiating phase. And from this sample picture, we have actually several possibilities of producing dark matter in an out of equilibrium state. One of them is the ultraviolet freezing via scattering. So essentially production of dark matter via annihilation of standard model particles. But there are essentially other couple of options. For example, there's the possibility, since we know that, well, since we assume that the standard model is being produced by the decay of the inflaton, we can also assume that dark matter is being produced by the decay of the inflaton itself. And a third possibility is that dark matter is being produced by the decay of some particle that could be thermalized or not with the standard model plasma. So this case was already discussed in the previous talk. So these 3 production mechanism essentially seems quite different, and as you can guess from the kinematics, you should expect essentially a different cosmology. But there is a common feature in all these scenarios, essentially that you produce all the dark matter in a very early stage of the universe, and once production stops, essentially these particles only interact via gravity, and they don't interact with themselves, they don't interact with the standard model with any other interaction than gravity. So the question is, what is the cosmological signature of this kind of hidden scenario? So in order to characterize the cosmological impact of these scenarios, we need to take care of the phase-space distribution of the dark matter. So Kathleen already said a few words about this. So let me just remind you essentially what it is. It is essentially the quantity that allows to compute, for example, the number density or the energy density as integral of this phase space distribution. And essentially, the time evolution of the phase space distribution follow this Boltzmann equation, where on the left-hand side, you have essentially a term that determines the time evolution, the terms which is responsible for, which account for the Hubble expansion. And on the right-hand side, you have the collision term, which essentially tells you how various interaction processes will affect the dark matter phase space distribution. So once you have computed this collision term, you can determine the phase space distribution by simply integrating this collision term. The only subtlety that you need to take into account, you need to take into account the redshift between the time of dark matter production and the time at which you evaluate the phase space distribution. So this is what this ratio of scale factors here accounts for. So as we said, since we assume that dark matter is being produced in the early stage of the universe, at some point production stops, meaning that the collision term vanishes. So after this time, essentially you have a zero on this right-hand side here, and the dark matter phase space distribution only follows redshift with the universe. So from this moment, you can express the phase space distribution as a function of a unique quantity, which is called the co-moving momentum Q, which we can express as the product of the momentum times the scale factor. And here we introduce just this dimension-full scale, T star, that allows essentially to rewrite the number density as an integral of my phase space distribution expressed in terms of Q and this quantity. So for those who are used to work with the code class, this quantity is simply what is called T and CDM. So let me just give you an example without going too much into details about how essentially we can compute these things. So let's take the example where, for example, dark matter is being produced by perturbative decay of the inflaton. So let's assume that an inflaton particle phi decays back-to-back to two dark matter particles. In this case, the collision term can be expressed as this rather simple formula, which is quite intuitive, since it depends on the dark matter, the inflaton decay width, the branching fraction to dark matter, the inflaton number density, and this delta Dirac distribution, which ensures that the momentum of outgoing dark matter particles must be the mass of the inflaton divided by 2. So from this, we can actually, as I said, we can integrate this collision term and compute the phase space distribution that can be re-expressed in this way. So it's not really important, all these factors. What is important is that we factored out the momentum dependence of this expression. And in our case, we can express this quantity T star as being some relativistic degrees of freedom times the inflaton mass divided by the releasing temperature. And this is the photon temperature at the present time. So just to give you an idea about what this distribution actually looks like. So this is what we have computed using 3 possible techniques by doing an analytical approximation, a full numerical computation, but also doing a fit. And we can see that this function can be actually quite well fitted by these relatively simple formulas that go as a power law of the momentum and then that decrease as an exponential. So essentially from this mechanism, we're able to compute the phase space distribution. And we actually repeated this exercise for various possibilities of producing dark matter that I described previously, but also in other cases. And what's essentially what we get is this picture. So this is essentially a cartoon that shows various dark matter phase space distribution depending on the production mechanism. So here, for example, you recognize the inflaton decay case that I mentioned, and this essentially tells you more or less when dark matter production occurs. So in various cases, you can see that we actually get quite different phase space distribution. And actually, what we have seen is that in our paper, we have seen that most of this distribution can be well fitted by a quite simple formula. So as I said before, just a function that goes as a power law first and then decreases as an exponential. So in all these cases, we have computed the phase space distribution. And now the idea is to say, what can we say about dark matter? What is the cosmological imprint of this kind of out of equilibrium dark matter scenarios? So this is what brings me to my second part. So essentially, the cosmological role of this out of equilibrium dark matter candidates will be essentially triggered by 2 quantities, the energy density and the pressure. And both of them can be expressed in terms of this phase space distribution. So in terms of integral of this phase space distribution, here and here. I just remind you that we define the co-moving momentum as being just roughly the momentum times the scale factor. And once we have computed our phase space distribution, we can compute both quantities, the energy density and the pressure. So we can define an equation of state parameter, which is just the ratio of these two quantities. Just to remind you that in the pure lambda CDM framework, the equation of state parameter of dark matter is precisely set to 0. So this is actually what cold mean in CDM. Cold mean pressure, meaning that we completely neglect the pressure component of the dark matter. But in our case, we have computed the phase space distribution, so we can compute the pressure. And a priori, since our phase space distribution is not 0, we shouldn't expect the equation of state parameter to vanish. So this essentially leads us to consider non-cold dark matter cosmology. And by non-cold dark matter cosmology, I mean to look at the cosmology of a dark matter candidate which has a non-vanishing equation of state parameter. So essentially, how to see the impact, the cosmological impact of this kind of dark matter candidates. So essentially, we will do what we essentially usually do in cosmology, is that we expand all quantities in terms of a background quantity that depends only on time, plus a small fluctuation that will depend on space. And once we apply Einstein equation to these quantities, Einstein equation will relate the homogeneous part of this phase space distribution, which characterize the energy density to the expansion rate of the universe, and the small fluctuation will be connected to the metric fluctuation. By doing a bit of algebra and a couple of assumptions, essentially, we can show that from this picture, in the matter domination era, we can show that the matter over densities, delta here, will follow a rather simple equation, rather simple differential equation. And in this case, we assume that the equation of state parameter must be quite small, but not 0, because we know that dark matter cannot be too different from lambda CDM, because lambda CDM is a very good description of our universe. So as you can see in this differential equation, which is expressed in Fourier space, there is only one term which depends on the Fourier wave number. And we introduce this quantity, which is the free streaming wave number, which depend on the equation of state parameter. But actually, when this equation of state parameter is 0, so which is the case for cold dark matter, you can see that this equation doesn't depend on the Fourier wave number, meaning that all the other densities in the matter domination era will rise regardless of the value of the wave number. However, if we consider an equation of state parameter which does not vanish, we should expect to see a cutoff in the power spectrum at a scale which is determined essentially by this free streaming wave number. And as you can see, this quantity depends only on the equation of state parameter. And this is actually very important, is that the quantity that controls the cutoff scale in this kind of scenario is not the precise shape of the distribution, it's the equation of state parameter. So, as I said, in this kind of cases, we should expect to see a cutoff in the power spectrum. So we already have, by Kathleen, a very nice, essentially, review on Lyman alpha and warm dark matter, so I'm not going to enter into details. I'm just showing here on the left the matter power spectrum as function of the Fourier wave number. In black, it is the lambda CDM expected value. And you can see all the measurements, including the Lyman alpha points on the far right. And as you can see, also plotted in red, what you will expect if you take a warm dark matter candidate with a mass of 100 eV. So as Kathleen said before, warm dark matter is just essentially a benchmark scenario so that people actually use, for example, to set bounds on, because it's rather simple. It depends essentially only on two quantities, the warm dark matter mass and the warm dark matter temperature. Essentially, once you fix the rate density, you fix one of these parameters, so you only have one free parameter left. So this has been used by Lyman alpha actually to set bounds on the warm dark matter mass. And as Kathleen said before, essentially this bound lies roughly around the scale of 3 keV. So of course, it depends a bit depending on the analysis and the underlying assumptions. But as I said before, since only the equation of state parameter triggers and control the cutoff scale, we can convert the bound on this warm dark matter mass to a bound on the equation of state parameter. And you can see that Lyman alpha actually constrains this equation of state parameter to be of the order of 10 to the minus 15, which is an extremely small number and essentially tells you why lambda CDM is such a good description of a universe, because the equation of state parameter of the dark matter has to be very, very small. So dark matter has to be very cold. So we know essentially the bound on the equation of state parameter for the warm dark matter. The question is how we can essentially rescale this bound for all our scenarios. So as I said, since only the equation of state parameter will control the cutoff scale, we just found the precise dark matter match, the precise dark matter mass that gives an equation of state parameter, which is the same as the one that is constrained by Lyman alpha. And essentially, we can actually show with a bit of algebra that we can express the equation of state parameter in our case. So if we assume that dark matter essentially doesn't interact with itself or with the standard model other than gravity, we can express this equation of state parameter in terms of very few parameters. This quantity T star that I used to define my co-moving momentum, the second moment of the dark matter phase space distribution, and dark matter mass and scale factor. And by using this equation of state parameter matching procedure, we can rescale the bound on the dark matter mass for any given dark matter scenarios. And we can express it as the bound from Lyman alpha on the warm dark matter. And the only quantity that I need to know here is this quantity T star that is used to define my co-moving momentum and the second moment of the distribution. As an example, if you take a phase space distribution which can be expressed in this way, so as something that goes as a power law and then decreases as an exponential, by using this procedure, you can get an analytical rescaling of the bound from Lyman alpha on warm dark matter to your favorite scenario. So essentially, this is what we determine analytically. The question is, does it actually work numerically? So in order to check this, we actually computed numerically the power spectrum. So here we represented the transfer function, which is just the ratio of the power spectrum divided by the expected value from lambda CDM to the power 1/2. And by using our equation of state parameter matching procedure, we predicted the mass of the dark matter for a given phase space distribution that should give me the same cutoff in the power spectrum than warm dark matter. So essentially, we have three values here because we had essentially three ways of determining this phase space distribution. So by doing analytical computation, full numerical computation of it. And so we predicted these masses, we computed numerically the power spectrum, and we compared with the numerical prediction of the power spectrum with for warm dark matter candidate with a mass 3 kb. And as you can see in this curve, all the curves lies almost precisely on top of each other, showing that this actually matching procedure works quite well. So now that we know essentially how to rescale this, the bounds in all our scenarios, we can try to look at the phenomenological consequences in this kind of framework. And so I'm taking again this, this scenario where dark matter is being produced by perturbative inflaton decay. And by using our procedure, we can rescale the Lyman alpha bound on warm dark matter in our scenario. And we essentially get this formula. So something which depends on relatively few parameters, number of entropic degrees of freedom, the inflaton mass, and the reaching temperature. And you can see that already from this choice of parameters, if you take a bound from Lyman alpha of the order of 3 kV, as essentially shown in the literature, you get already a bound which is 3 orders of magnitude more in this case. And what is very interesting is that if you take a very small reaching temperature, which can be in principle as small as maybe 10 MeV or even less, you can see that the bound on your dark matter candidates become as large as the EV scale, meaning that if you think naively that that this bound should be at the KV scale, you are off by 10 to the 8 or so order of magnitude. It's actually showing how Lyman alpha can be actually quite strong to constrain this kind of scenario. Now, if you require that your dark matter candidates essentially fulfill the rate density condition, you end up with a constraint of the branching fraction of the inflaton to dark matter to be this value. And what is very interesting here is that it depends only on extremely few parameters. So you just pick your favorite value from Lyman alpha here. Essentially, this quantity is the number of entropic degrees of freedom, which cannot be too different from the standard model expected value. And you get already a constraint from this branching ratio to be smaller than 10 to the -4, which is actually quite small. So this shows that actually Lyman alpha is able to probe dark matter interaction with the inflaton, which is actually quite nice in the sense that this kind of essentially coupling is extremely hard to probe. What is interesting is that even if in your specific model you don't have a coupling between the inflaton and dark matter, as soon as you assume that dark matter interact with the standard particles, then you would expect the inflaton to be able to decay to dark matter via this kind of loop-induced process. It's actually quite nice and a bit more general. And then you can play essentially with...
We have to come to an end. I don't know whether you saw my messages or not.
Ah, no, sorry. Okay.
If not, then this method doesn't work, but we have to come to an end. Sorry.
Okay. I'm stopping here. So essentially, you can play the same game for various production mechanisms, and you can see what are the phenological consequences. Okay, so I'm just concluding. So I hope I convinced you that there are a couple of possible ways of producing dark matter in an out of equilibrium state, that in all these cases, we should expect a cutoff in the power spectrum, which is probed by Lyman alpha. And I hope I convinced you that Lyman alpha is an extremely powerful tool to probe this kind of scenario. And you can have a look at the paper and see essentially more results. That's it. Thanks.
Okay. Thanks a lot, Matthias, for this interesting talk and the interesting conclusion. Dark matter is cold. Very good. Andrew, please go ahead.
Hey, maybe you covered it in the like, and I missed it, but on slide 9 you have this constraint on the omega parameter of warm dark matter in terms of A, which I assume is a scale factor. At what is that the scale factor, and at what point in, like, when is that scale factor?
So,
if you know what I mean.
Right. Okay. I see. Yes. So yeah, essentially, this scale factor has to be evaluated at the present time. So in this kind of cases, the equation of set parameter goes as a to the power -2, but here it has to be evaluated at present time. Yeah.
Okay.
Sorry, that's that's not clear.
No worries. Thanks.
Okay. Any other questions for Matthias? This is not the case. Then thanks again for this interesting talk. And we come to our third speaker, Vera. Okay. Please try to share your slides.
Sure, thank you. Can you see my slides?
Yes, full screen would be even better.
Okay, let's see if that works. Is that good?
Yes, that's perfect. So,
perfect.
Constraints on dark matter from galaxy formation. Vera, please go ahead.
Yes. Thank you guys for having me. I'm really excited to share some work from both me and my collaboration. I wanted to highlight a grad student in my collaboration who's actually going to be on the job market, who has been pivotal to some of the self-interacting dark matter stuff that I'll be talking about at the end, Akasha Cruz. So if she applies to a job with you, take a good look at her application. She's fantastic. So today I'm going to tell you about dwarf galaxies, and in particular, the tiniest of dwarf galaxies, ultra-faint dwarfs. And in this movie that I'm showing you the formation of a dwarf galaxy. And if I go back to the beginning, the green is the dark matter, and we're watching baryons collapse into these small halos, and they will merge to form a bigger halo. But what you can see is the yellow and the red, and that is exploding gas out of these halos. And this is a very violent process. And so the reason I start with this video is to drive home the point that if we're going to model in galaxy formation simulations, dwarf galaxies, it's important to also model the baryonic processes that go on within these galaxies, even though, as Katwin said, they are extremely dark matter dominated. So just to define my terms, I'm going to be talking about galaxies, which are collections of baryons, stars, gas, and dust, all contained within a dark matter halo. And dwarf galaxies, in my definition, are any galaxies that are smaller than the Milky Way. So in this image I'm showing you, the Milky Way is in the center, and in its neighborhood are satellite dwarf galaxies, for example, the Large and Small Magellanic Clouds. So dwarf galaxies are important because they have presented some challenges to the cold dark matter model that people commonly adopt for the most part. And some of these crises at these small dwarf galaxy scales are shown on this scorecard that I have in front of you. I don't have time to go through all of them, but The starting assumption of this talk is that I don't think that there is a small scale crisis for CDM. And in particular, that's because when you model the effect of the baryons, in particular that feedback that I showed you in that movie, you can solve the majority of these small scale challenges. This does not mean that cold dark matter is the right dark matter model. Warm dark matter and self-interacting dark matter are just as exciting. In fact, warm dark matter and self-interacting dark matter on their own, without baryons included, can solve a lot of these small scale problems. But here is the problem, right? If you include baryons in all of these dark matter models, they all solve all these problems. So the question becomes, how do you tell these things apart? So in the recent 10 or so years, so in the last decade, the number of dwarf galaxies that we've been finding has exploded, right? So if you look from 2010 to 2020, we've increased from 10 to 60 dwarf galaxies. And most of these galaxies that we're finding are what are called ultra-faint dwarfs with stellar masses below 10 to the 5 solar masses. And I argue that this is only going to continue. So in the advent of the Vera Rubin telescope and JWST and the Roman Space Telescope, we're going to find a significant amount of these even more. So this explosion in dwarf galaxies is going to continue. So studying these galaxies and understanding them in the context of dark matter is something that's very timely and very exciting. So the key problems that I'm going to try to address in the short talk that I have is, can we continue to understand formation and evolution of dwarf galaxies, in particular these ultra-faint dwarf galaxies, in this vanilla CDM plus baryon model? And is there a smoking gun that might differentiate CDM from some of these other models that I showed on my scorecard? So why ultra-faint dwarf galaxies? So we'll start with the bullet points. They're considered really simple systems astrophysically, right? They're very old in terms of their stellar population. Reionization truncated their star formation. So, that's quite simple. They're the most dark matter dominated of the dwarf galaxies. So we assume that dark matter kind of dominates their structure and their properties. However, because they're so faint, this might be difficult to measure. And we know that counting them can constrain the smallest dark matter halo that can host a galaxy, and maybe dark matter, as Caitlin shared in her overview talk. And so on the right, I'm showing you this cool, plot of all the different gravitational constraints for dark matter as a function of halo mass. And what's really neat about ultra-faint dwarf galaxies and dwarf galaxies is that you're moving from the visible to the invisible. And so understanding these and where they go dark kind of pulls you down in halo mass and into the regime where maybe there are no more galaxies to see and you just have these empty dark matter halos. So like there's been an explosion in dwarf galaxies that we're finding in our neighborhood, I'd say simulators have gotten really good at simulating dwarf galaxies. So in my group, we've gathered together a suite of 211 simulated dwarf galaxies. So there are ultra-faint dwarfs and dwarfs in isolation in the Marvelous Dwarf Galaxy suites. And then we have the DC Justice League, which contains 4 Milky Way-like galaxies named after the first 4 women Supreme Court justices, and all the dwarf galaxies in their neighborhood. So these are dwarfs and ultra-faints in the vicinity of the Milky Way. So simulations are now able to make predictions across the whole dwarf mass scale, now including ultra-faint dwarf galaxies in multiple environments. So in isolation and in the neighborhood of the Milky Way, which is analogous to kind of what we're finding now observationally. So with this mass resolution, we're really probing these faint systems down to magnitudes of -2, stellar masses of 1,000 solar masses. So what can we do with these simulations? What can we learn from these simulations? Well, what we can do is try to constrain the mass function, right? Because one of the things that's going to happen with Rubin, with Rubin and with JWST is that we're going to push the mass function down to fainter and fainter masses. The question is how sensitive are our simulations to the choices that we make in terms of how we model them, in particular, how we model those baryonic processes, which are really important, and including star formation and feedback. And so some work a couple of years ago, I took one of the Marvel dwarf volumes, and with the same initial conditions, all I changed was the way that I formed stars. So I picked one way to form stars on the left, one way to form stars on the right. And what you can see is that there are different numbers of star symbols. And those star symbols are ultra-faint dwarf galaxies. So if you translate this into a mass function, which is the bottom plot on this slide, so we have stellar mass on the x-axis, number count on the y-axis, you can see that star formation model matters. If you compare the orange line to the blue and green line, you can see that we predict in this gray band, which is the DES survey discovery space, different numbers of dwarf galaxies. So if we want to use galaxy formation simulations, in particular, ones that include baryonic physics, your predictions are very sensitive to the choices that you make. And this wasn't the case when you were considering larger dwarf galaxies. So why is that? It's because ultra-faint dwarf galaxies are unable to self-regulate. There we go. So what's going on here? What do I mean by an inability to self-regulate? At higher masses, what essentially happens in your dwarf galaxy is that everything evens out. Your dwarf galaxy is forming stars for its entire life, and it's undergoing star formation bursts and feedback bursts, and all of that kind of averages out over that long period of time that it's forming stars. In an ultra-faint dwarf galaxy, that is no longer the case because you've formed your stars very rapidly, very early on, so you don't have that long time scale to average over, and so you become incredibly sensitive to the way that you form stars and the way that you incorporate feedback in your galaxy formation model. So some of the consequences of the inability to self-regulate means that we predict different star formation histories for ultra-faint dwarf galaxies that all are in the realm of plausibility observationally, and it's incredibly difficult to tell them apart. So what I'm showing you here are 4 different star formation models. I'm not going to worry about the details of these star formation models, but you can see that some of them form their stars very early and in a quick burst, and some of them have delayed onset of their star formation. Okay, so the question is there a way for us to constrain our galaxy formation simulations so we can make predictions about the low mass end of the mass function? And so what actually might be the key is looking at the metallicities of these dwarf galaxies. So on average, how much iron is there locked up in the stars in the dwarf galaxy? And so what you're seeing here is for all these different metallicity models, on the left, the total metallicity of the halo as a function of the brightness of the galaxy, and on the right, the width of the metallicity distribution function of the galaxy. And if you squint at this, you might be able to see that if you compare to the observations, which are in black and gray, that some of these models fit the observations better than other models, but none of them seem to fully fit these observations. However, in terms of making constraints, this seems like the most promising route. All right, so I'm bringing us back to this plot, which I didn't fully explain when I initially put it up. So what we're looking at here is the stellar to halo mass relationship for all 211 dwarf galaxies. And on the left, we're looking at halo mass at z=0 versus stellar mass. And on the right, we're looking at peak halo mass, so the maximum halo mass of a halo versus stellar mass. And what you can see is that there's a lot of scatter, right? The scatter at a redshift of 0 is probably due to dark matter stripping because a lot of these dwarfs live in the vicinity of a Milky Way, and so they've undergone significant stripping of their dark matter halos, but there's still some intrinsic scatter if you consider the maximum halo mass, that peak halo mass. And so in order to constrain kind of where galaxies go dark, we have to understand the scatter in the low mass end of our stellar to halo mass function. And one thing that I want to point out is that that scatter grows as a function of mass. So it starts out really small, and by this ultra-faint dwarf galaxy halo mass range, that scatter is on the order of 1 dex. And so if you put that into predictions for a mass function, right, this scatter that grows as a function of halo mass, it does change the slope of your mass function. Now you'll notice that this does not look as big of a change as the one that we see with our star formation model. And that's true, right? Our predictions are much more sensitive to the star formation model, but the scatter is a non-negligible effect. In particular, if you imagine extrapolating these to lower and lower masses, those two lines are going to diverge even more. So can we continue to understand the formation of ultra-faint dwarf galaxies in a vanilla CDM plus baryon models? Yes, most likely, but it's getting really difficult to do so using galaxy formation simulations because of ultra-faint's inability to self-regulate. But I want to be clear here, I'm not favoring cold dark matter, right? I'm just saying that for any dark matter model, we've really got to understand the baryons, and that is getting increasingly difficult to do. And there's some observations we can chase to try to constrain this, but this is something we really need to be thinking about as galaxy formation simulators as we start to make predictions for these upcoming missions. So I'm saying that CDM is not correct, and I want to share some of the work that we've been doing in galaxy formation outside of cold dark matter. So one of the things that we've been looking into is simulating dwarf galaxy formation with baryons in these zoom in simulations, and in particular looking at the shapes of these dark matter halos. So dark matter halos in SIDM, because of the interaction of the dark matter particles, tend to be very spherical, whereas in CDM they tend to be more oblate. Stars follow the shape of their dark matter halo, so the shapes of these dwarf galaxies could be an indicator to tell SIDM apart from CDM in a way that's measurable with, say, the Roman Space Telescope.
You have about 2 minutes left. Yeah.
Okay, so this is just an example of some of the fitting that we're doing to measure shapes. So I'm going to zoom by this. And another thing that I've been thinking about is the fact that we know now that dwarf galaxies host black holes, massive black holes, and we know that sometimes these black holes are off-center. And the reason that some of these black holes are off-center is because of core formation in dwarf galaxies. The way that cores form, the sizes of these cores, and the distribution of offsets is going to be sensitive to dark matter model if you're considering CDM versus SIDM. And so looking at black hole offsets in dwarf galaxies might be another way to constrain SIDM versus CDM. So I'm bringing you back to my conclusion slide. Galaxy formation is really hard. Even these simple ultra-faint dwarf galaxies are incredibly difficult to simulate because of their inability to self-regulate. And so a lot of work needs to be done in order to model baryons in a way that we can trust in order to interpret that influx of data that we're about to get from JWST, Ruman, Roman, and even Lisa. So with that, thank you, and I'll take questions.
Okay, thanks. I didn't even have to announce the 0 minutes. Thanks for being on time, and thanks for this indeed very interesting talk. Shema, you have a question.
Yes, hi. Very interesting. Thank you for the talk. So you mentioned briefly, the role of tidal forces, and my question is related to that. I mean, in order to interpret the observations, we will need to distinguish also, we'll have to pay attention to the environment where these dwarf galaxies are and understand the role of that environment in the structure of these galaxies. Is that something that is being studied in detail, or is like a second?
Yes, that is such a fantastic question. I am actually with Charlotte Christensen working on exactly this. So we were looking at the role of environment in the stellar to halo mass relationship. So is there a difference in how these dwarf galaxies populate their dark matter halos in isolation versus in the environment of the Milky Way, which is, you know, kind of what we're probing right now. And in isolation is what we're going to probe in the future. And it turns out there is in fact a difference, in particular at higher dwarf masses where it's not blurred out by scatter, between the slope of the stellar to halo mass relationship in a Milky Way environment versus in isolation. And essentially, this has something to do with the way these dwarf galaxies assemble in their various environments. In isolation, you assemble later, so your stellar masses tend to be smaller, whereas in the environment of the Milky Way, you assemble more quickly. And so you get, for a given halo mass, more stellar mass. And so stay tuned. We're working on that paper right now.
Very good question and very interesting answer. Are there more questions? Maybe I have a little curiosity, just because I see it here. You mentioned several space telescopes that can be used. You mentioned here James Webb, Roman, and Rubin. You also mentioned LISA. I don't remember LISA in your talk. Maybe I overheard it, but how does LISA help you here? Yeah.
Yes, so I would point you to Bellavery 2019. So Jillian and I looked into using these simulations, the merger rate of massive black holes in dwarf galaxies. Mm-hmm. And that has to do with how many of them are in the centers of their halos versus offset. And so that distribution changes in SIDM versus CDM. So those merger rates are going to look different.
Okay.
And that is something that we showed in that paper is very detectable in that waterfall diagram for LISA.
Okay, curious, because normally the black hole mergers or so, the rates are now detected by LIGO, Virgo, etc. Yeah, but that they move out of that range. Okay.
Yeah, so these are massive enough that you'll need, these happen at high enough redshift and are more massive than like stellar mass black holes. So they are in LISA's parameter space and not in LIGO.
Hopefully they don't give too much background then for the other investigations. Okay, I don't see any further question. Then thanks again to you and the other speakers. We'll take a break now and we will meet again at 10 minutes to 6 in 18 minutes, or 10 minutes to 6 here in Santander time or European Central Time. 18 minutes of break. Okay, thanks. Joe, go ahead, please.
Hi, this is Sven.
Yes, this is Sven.
Hello.
Hi there.
Okay, can I share screen?
Yes, you can share the screen now.
Okay, I think this looks like it's going to work actually pretty simply.
Normally it works.
Just make sure I get the right slide.
Now we see your whole desktop.
Sure. And you can see my first slide now, I think.
Moment.
Perhaps not. Oh. Okay, good.
Yes, our dwarf galaxy is a challenge for Lambda CDM.
That's right. That's right. Okay, great. Okay, very good. Okay,
so I
that's
see
all
that you are prepared for the round table. Very good.
I just going to show 4 slides. That's all.
Yeah,
so just
perfect.
to focus people's thoughts.
Very good.
And
okay.
It's interesting.
The connection is breaking up a bit, but right now it's not that important, I guess. Okay.
Okay.
Yeah. Okay. I'll take a little break as well.
Okay.
Hi, Sven. Can I test my setup?
Of course you can. You are welcome.
Thanks. Okay, video looks fine. And then this, and then, oops, wrong one. Okay, yeah, all good?
Yes. Can you go one slide ahead?
Sweet.
This looks good. Perfect, Andrew. Very good.
Okay. And also, how's my volume? Is that fine?
Your volume is fine. Yeah, I hear you
Okay,
perfect.
sweet. Excellent. Thanks.
Okay, good. See you soon.
See you.
Elisa, I just wanted to check whether you're here. Very good.
Hi.
Hi. Can you show us your slides, please?
Yes, sure. Can you see my screen?
Yes. Now full screen. Okay, one slide ahead, please. Okay, everything works. Perfect. Very good.
Okay.
We'll start in about a minute, yeah?
Okay, should I leave it here or?
Yeah, leave it there.
I
Then
take
people
that?
can
Okay.
familiarize themselves already.
Okay.
Very good. As the others, you have 17 minutes and I'll give you a 2-minute warning. Yeah?
Okay, yes, thank you.
This is your laser pointer, I suppose, yeah? That I can see flying around.
Yes, yes, it's mine.
Okay, very good. So it's time, 10 minutes to 6. Let's get started. We have Elisa Tau here, and she will talk about dark matter deficient galaxies and the simulations they're doing. Okay, Elisa, please.
Okay, thank you. Hello, everyone. Thank you for having me. My name is Elisa Tau. I recently graduated from the National University of La Plata in Argentina, and now I'm currently a first-year PhD student at the University of La Serena in Chile. And today I'm going to talk about my work under the supervision of Claudia Scoccola, where we studied dark matter deficient galaxies using hydrodynamical simulations, specifically Illustris-TNG. So in my talk, first of all, I start giving the context and motivation that drew us to study this type of galaxies. Then I'll talk about the methodology and characterize the sample that we studied. And afterwards, I'll show our results, and I'll finish summarizing and concluding our work. So first of all, as we all know, in the lambda CDM model, dark matter is the dominant mass budget of the universe. So even low mass galaxies are expected to be dark matter dominated, well, at least within their central regions. But recently, there have been some observations that suggest that some low mass galaxies may have low dark matter fractions. And so these galaxies would be dark matter deficient, according a definition I will tell you just following this slide. And this is why we wanted to study these galaxies. They are really rare and interesting. And there have been some studies in the literature that address this problem using hydrodynamical simulations such as EAGLE, Illustris, and recently New Horizon. But in this work, we used Illustris-TNG to study dark matter deficient galaxies. And Illustris-TNG is a hydrodynamical simulation in which the dark matter particles and the baryonic particles are followed. Their evolution is followed. And well, there are 3 boxes that you can use of volumes, cubic volumes, roughly of 50, 100, and 300 megaparsecs in side length. In this project, we used TNG 100 at different redshift, the data at different redshift, such as redshift 0, 0.1, 0.4, 1, and 2. And we studied dark matter galaxies in those redshifts. and afterwards we used Illustris TNG 50 only at redshift 0 to study this type of galaxies as well, because it has a better resolution. So dark matter fraction is measured as the ratio between the mass of the dark matter that a subhalo has and the total amount of its mass. And then we have dark matter deficient galaxies as those with a dark matter fraction below 50%. And in this work, we calculated the dark matter fractions using two different criteria. One is using the total amount of mass that the subhalo has, and the other one is using only the mass that is located within the central region of the subhalo. And for that, we used the stellar half-mass radius, well, twice the stellar half-mass radius. And well, this is the sample in Illustris TNG 100. We have the halos that are found using a friend-of-friend algorithm and the subhalos that are found using a subaffine algorithm. And in Illustris TNG 50 at redshift 0, we have more halos and more subhalos due to its better resolution. And when we studied the dark matter fraction of these subhalos within their central region, we only considered those subhalos that have a defined stellar radius. So we could have the total amount of mass in twice this area. So here are some results. First of all, using TNG 100, we found a small percentage of galaxies that are dark matter deficient because they have a dark matter fraction below 0.5 at each studied redshift. Here you can see the total amount of subhalos that were considered at each redshift, and then in this other column, you can see the amount of dark matter deficient galaxies that were found at each redshift. And then in these two other columns, we have the number of considered subhalos that have a stellar half-mass radius defined, and the number of dark matter deficient galaxies using this criteria. And as you can see, if we use the mass that is located inside the central region of the galaxy, you can find more dark matter deficient galaxies than if you use the other criteria when you consider the total amount of mass that a subhalo has. And some of these galaxies could be tracked down up to redshift 1, but none of them could be tracked down up to redshift 2. And then we reproduced the same analysis, but for Illustris TNG 50. Here we only studied redshift 0, and as you can see, we also found dark matter deficient galaxies using both criteria. So we then wanted to study the dark matter fraction using both criteria. So we compared it, plotting the dark matter fraction using the total amount of mass of the subhalo and the mass within its central region. Here we color-coded their masses, their total masses. And as you can see, the dark matter deficient galaxies that meet both criteria are have low masses. They are not very massive galaxies. Whether the ones that are only dark matter deficient when considering their central region are more massive. This is for TNG 100, and the same can be seen in Illustris TNG 50. So we then proceeded to study the subhalo mass function at redshift 0 for Illustris TNG 100 and Illustris TNG 50. And as you can see, these are the green one is the subhalo mass function for Illustris TNG 100, and this one is for TNG 50. And as you can see, there are more low mass subhalos present in TNG 50 because of its better resolution. So these results when considering low mass galaxies are more reliable than the ones that you can get when using TNG 100. And we then studied the subhalo mass spectrum for those subhalos that are dark matter deficient galaxies, and again for both boxes. And we only selected those galaxies that have a cosmological origin. So as you can see, the red one is for illustrious TNG 100, and the orange one is for TNG 50. And the one of TNG 50 is higher because it has a better resolution. So the loss of dark matter that a subhalo suffers, a dark matter deficient galaxy suffers, can be followed with more detail and more precisely than in TNG 100. So once we got our sample of dark matter deficient galaxies, we wanted to study their evolution to get to know a possible explanation for their formation. And here I'm showing as an example one of them. This is a dark matter deficient galaxy, and the first redshift that you can see here is the redshift at which this subhalo is accreted by a central subhalo. So this galaxy will start being a satellite galaxy. And in the first panel, you can see the distance between the satellite galaxy and its host halo, its host subhalo. And as you can see, as they approach each other, the dark matter fraction decreases. So this leads us to think that there could be a tidal stripping scenario taking place, and this dark matter deficient galaxy at redshift 0 would originally form with a normal amount of dark matter, and then it would lose it along its evolution. As you can see, when the satellite galaxy is accreted, it has more mass than it has when you take it into consideration at redshift 0. So this galaxy could be losing its mass due to tidal stripping. And here I'm showing the same evolution, but for another galaxy using TNG 50. And you can see that the same thing happens when they approach each other. This dark matter fraction decreases, so you could explain it with a tidal stripping scenario. And then we also studied those subhalos that are dark matter deficient when considering only the central region of the galaxy. So here we have the same explanation. We know that when they are created, they have a mass that is much higher than at redshift 0. And their dark matter fraction also decreases when they approach their central subhalo. You can also see in the other two panels the evolution of the baryonic mass and the dark matter mass. And this one was accreted at redshift 1.2, and this one at 1.21. This one is was studied using TNG 50, and again, they are not the same galaxy. This one is a different galaxy studied with TNG 100, and this one is a galaxy studied with TNG 50. The same thing happens with its mass. It starts being more massive, and then it loses its mass through its evolution. And this dark matter fraction also decreases, and there is a general decrease in mass when they approach each other. So in this work, we are proposing the scenario of tidal stripping due to the central subhalo. And so these dark matter deficient galaxies at redshift 0 would start forming with a normal amount of dark matter, and then they would lose it along their evolution. So these galaxies do not present any, originally, any problem in the lambda CDM framework because they would start being dark matter dominated. So to sum up, we have found that dark matter deficient galaxies are allowed in current galaxy formation models, as we have shown in these simulations. The population of subhalos that are dark matter deficient when you consider both criteria have low masses. They usually have low masses, so they would be low mass galaxies. And the dark matter fraction decreases mostly when the distance between the subhalo, the dark matter deficient satellite, and the host reaches its minimum. So along its orbit, when the distance is the minimum, the dark matter fraction decreases mostly. And this, a tidal stripping scenario is well suited to explain this. And lastly, the subhalos that present dark matter deficiency when considering their central region do not necessarily lose their dark matter fraction, but instead it's replaced, it's not placed in their central region, but maybe in their outer halo. So they are not actually dark matter deficient. They are just deficient within their central region. And that's it. That concludes my talk. I think I'm in time. And thank you very much for listening.
Perfectly in time. Yes, thanks a lot. Now I have to read this.
Thank you for your attention. I'm happy to answer questions.
Yes, thanks a lot for this really interesting talk. I would have several questions, but no. There was a hand up by Andrew, but maybe this was an old one. I don't know.
Oh no, I was applauding. Sorry.
Ah, you applauded. Okay. Yes, very good.
Thank you.
Okay. So while maybe others are warming up, just this point that you were mentioning that the dark matter is stripped, yeah, then it should also be possible that you find this dark matter somewhere else where there's then too much, right?
You mean in other galaxies or in the same
galaxy? Or
galaxy?
you say maybe more in the outer parts of this galaxy or so, yeah, but the dark matter should be there. You say they start with a normal amount and then it's stripped, either being somewhere on the outer part or, yeah.
Yes.
It should be possible to see this larger density of dark matter somehow to confirm this or to test this, right?
Observationally, you mean?
Yes.
Yeah, I guess so, but I know it hasn't been observed yet. But galaxies do have a dark matter halo. They have the central region that has a lot of baryonic matter, and then this baryonic matter is less and less when you go to their outer regions. So they do have a dark matter halo that surrounds them. And well, the thing is that some of them do not have enough dark matter, considering this criteria, in their central regions, neither in their outer halo. That's what makes them interesting.
Yes, yes, definitely. But still, the dark matter should be somewhere if the idea with the formation is correct. Yeah.
Yes. We didn't study their central halos, their central subhalos with detail, but we checked that their amount of matter is increasing during its evolution. So maybe the satellite galaxy is losing matter and the central subhalo is secreting it, so it's robbing it.
Yeah.
And
okay.
So its mass is increasing, and its dark matter amount of mass is also increasing.
Okay, thanks a lot.
You're welcome.
I don't see other questions, strangely enough. Thanks again for this really talk.
You're welcome.
Our next speaker, Andrew, please share your screen.
Yep. Okay, yeah, we have everything.
Yes, this looks good. Okay.
Cool.
The interplay between primordial black hole effloration and dark matter production. Andrew, please go ahead.
Cool, great. Thanks for having me, everybody. Yeah, I've really enjoyed these few days. And yeah, so this talk is based on two papers that came out in July. And I produced them in collaboration with Lucien Artier, Yuba Perez-Gonzalez, and Jessica Turner. These two are based in Durham. Yuba was based, or is potentially still based in Fermilab, but is on his way to Durham as well. And I myself, I'm from the CP3 in University Catholic Leuven, but I'm speaking to you from AstroCent in Warsaw, Poland, which is where I'm going to start work in October. So, you know, there's been a kind of increase in interest in primordial black holes since the discovery of gravitational waves. And I'd say there are two kinds of categories which are kind of most interesting for dark matter physicists. And there's one case where the primordial black hole is stable, and that's when the primordial black hole's mass is greater than around 10 to the 15 grams. And in that case, it can contribute, these primordial black hole populations can contribute to the relic abundance of dark matter. And then there's the other case where primordial black holes are unstable and they evaporate before Big Bang nucleosynthesis, avoiding many constraints. And this is when their initial masses are around 10 to the 9 grams. And this is obviously what this talk is going to be about. And I just want to kind of take stock of things that we know about dark matter. And really, you know, as we all know, we don't know too much about it. We know that the nature and the origin is basically unknown. BBN and CMB basically tells us that dark matter was present very early on in the universe, and we have lots of particle models that often rely on some non-gravitational interaction between the standard model and dark sectors to produce the correct relic abundance. And this is drawn out by this cartoon here, where you can have you know, standard model interactions producing dark matter. You have the opposite. In the early universe, things are in equilibrium, and then eventually with the expansion of the universe, the dark matter species falls out of equilibrium and sets the relic abundance. Interestingly, primordial black holes could be a purely gravitational source of dark matter through Hawking radiation. And from this cartoon on the right here, you see that these the radiation or the production of these particles comes straight from these bubble diagrams, and they don't rely on anything other than the particle's existence, really. So I'm just going to do a bit of a review on black hole evaporations, okay? And so, as I said just now, the black holes evaporate particles irrespective of those particles' interactions. And here's the equation given for the emission rate of any particle, where E, mu, and P are the energy, mass, and momentum of the particle. And this sigma here is known as the absorption cross-section, and this describes the possible backscattering of those particles due to the gravitational and centrifugal potentials. And you have to, in order to determine that, you have to calculate, or you have to solve the wave equation or the particle equation of motion in the presence of a curved space-time. Often what's used as an approximation is known as is what's called the geometrical optics limit, and it's given by these sort of parameters here. So it's useful to define what's known as the reduced absorption cross-section, which basically measures the deviation that the actual absorption cross-section has from this geometric optics limit. And I say all this basically to point out the fact that that for different spins of the particle that you're interested in that's being created by a black hole and being radiated by a black hole, you have quite varying sort of behaviors. Okay, and when the energy of those particles that are being radiated goes to some high limit, it kind of approximates the geometric optics limit, but in the lower cases, there's some large deviations, and these are different for different spins. So it's another important thing to think about when you're interested in primordial black hole evaporation of stable particles, or any particle really, is that the particle mass is super important, because the black hole's temperature has to be large enough to actually produce those particles, to radiate those particles away. So when the mass of the particle is greater than the black hole temperature, the emission is suppressed quite a lot. So it basically goes to zero. And Hawkins showed that the temperature of the black hole is inversely proportional to the mass of the black hole, and also that the mass of the black hole evaporates with respect to time, or decreases with respect to time, by 2 powers of black hole mass in the inverse, sorry, 1 over mass of black hole squared. And that basically tells you that for a large portion of the black hole's lifetime, it's kind of plodding along at a similar mass to the initial mass value, but then it kind of dramatically evaporates. And also from this expression here, it tells you that the temperature stays roughly the same, but then dramatically goes to the Planck mass, which is when well, our understanding of the physics kind of breaks down. And that tells you also there are 2 separate regimes for particle production of stable particles, or any particle, but obviously we're interested in dark matter, so it's got to be fairly stable. And these 2 regimes are basically set by whether the mass of the dark matter is above or below that temperature, the initial temperature of the black hole. So if it's below the initial temperature of the black hole, the dark matter is being produced, or the particles are being produced throughout the entire span of the black hole's lifetime. Whereas if it's heavier than the initial temperature, the dark matter will only be produced when the temperature sort of is increases enough to start producing it. And these are the equations roughly, approximately, to how that behavior works. So of course, if we're interested in the production of these particles in the early universe, we have to track these evaporation processes in the expanding universe. So if people who are interested in doing sort of freeze in, freeze out, or any kind of mechanism of production of dark matter will know that these 2 terms on the left here, and on the right here, we just basically have a source term which is coming from the primordial black holes. Another interesting point of why these primordial black holes with sufficiently low mass are interesting is because the constraints that exist aren't strong enough to really exclude the possibility that a population of primordial black holes that evaporated early on could have dominated the universe at some point. In that case, it's quite important to actually track the development or the evolution of both the energy density of the primordial black holes in the universe, as well as the standard model, because primordial black holes not only will radiate standard model particles and reheat the universe, or the thermal bath of standard model particles. So here I'm showing what's called the beta parameter, which is essentially the fraction of primordial black holes over the total energy density of the universe. So here, and beta critical is when this value which determines whether the whether the primordial black holes ever dominated the universe. So here, when beta is greater than beta critical, you have primordial black hole domination at some point and then evaporation. And here, when beta is less than beta critical, you have just population of primordial black holes existing, but not really affecting the standard model BARF. So what we did and we presented in our papers was we created a public tool for calculating these systems and tracking these Boltzmann equations with primordial black holes in the yellow universe and generating stable particles. It's available on GitHub, and we tagged it onto Ulysses, which is a code originally developed for leptogenesis problems. And I encourage you all to check it out. So we have a couple of motivations for why we did this, right? So first of all, we thought that the full generality of dark matter production solely from primordial black holes hadn't been explored with as much precision as we would have liked. And this motivation one was what we focused on our first paper with. And what do I mean by precision? Well, basically, for example, evaporation is usually considered or assumed to be instantaneous, which seems like, from the plots I showed earlier, like a fairly good assumption to make, or like a reasonable assumption to make. But when you include a primordial black hole population which have spin, evaporation is more gradual. And also, when you're trying to calculate the relic density now, it's important to know what the temperature of the thermal bath was, which drives the expansion of the universe at that point. It's really quite important in terms of the value that you get is really sensitive to the temperature. So it's important to know how to really track how thermal plasma is being affected by a population of primordial black holes evaporating. So here I just show two plots of where we've tracked what happens to dark matter from black holes. We've tracked the kind of radiation, energy density of the standard model particles, as well as primordial black holes. And we've done it for two different sort of A star, which is the parameter which measures the spin of the black hole population. We're considering monochromatic black holes in all these plots, and we consider a spinless case and like an almost maximally spinning, because in this parameterization, one is kind of the boundary of what you can have for A star. So with this motivation, these small kind of effects that I explained in this previous slide, they could be quite significant when accumulated. So on the right here, I show a comparison with literature, where in the solid lines we have our full numerical evaluation, and on the left, or on the dotted lines, we have analytical solutions that we took from the literature. And the different colors basically refer to different dark matter masses. And what these lines are actually plotting out are the values of beta and initial mass of the black holes that are required if the mass spectrum is monochromatic, i.e. one mass and one spin. These lines basically tell you what beta you'd have to have in order to produce the correct relic density, relic abundance for dark matter. I should say that these are all Dirac dark matter cases on the right here. So spin half. And yeah, basically these differences come from the different evaluation of the temperature of the universe at evaporation, as well as deviations that Hawking radiation has from the black body spectrum. Our second motivation for developing this tool was because we really wanted to see what the interplay could be between interacting dark matter models and primordial black holes. And that was a focus on the second paper. And we thought it's important, I think it goes without saying that it's important to understand what kind of scenarios are inconsistent, i.e. what kind of primordial black hole sort of population would be inconsistent with certain WIMP dark matter candidates, for example. A way to pose this would be, could a future detection of dark matter constrain the primordial black hole fraction? And we've seen lots of different experiments over the last few days, which are trying to measure dark matter or which could measure dark matter, and they could potentially have interesting sort of statements about the primordial black hole population in the early universe, but we don't really know until we know how these things will kind of interact with each other. So I don't have much time, so I'm just going to like show up some highlights. These are two papers that I think are particularly worth mentioning. And
we have about 2 minutes. Yeah.
Yeah.
Andrew,
okay. Cool.
2
Thanks.
minutes.
Yeah. So we get a significant enhancement for spin 2 massive particles with high spinning primordial black holes. So this is near the maximal spin. And here I show on the left a similar plot that I showed to you before, where you have Schwarzschild black holes, so not spinning, against the near maximally spinning Kerr black holes. And we see here the spin 2 particles, the tensor dark matter particles, get a huge enhancement in certain regions of parameter space, just from the fact that you have a population of spinning black holes rather than not. I should also mention that these pale out regions here are basically to show when the warm dark matter constraints kick in for certain masses of dark matter. Okay, quickly, we look at extended dark sectors by adding more particles that decay into dark matter, and that's quite interesting as well. And then for the second paper, we fully track the sort of the distributions and the number densities of all the particles in the situation with coupled Boltzmann's equations. We track it throughout the expansion of the universe, and we consider in that case just a simple U1 mediated Dirac dark matter case, and that's super interesting. But as you can tell, I didn't have that much time. We focus, allows us to systematically look at regions where there's an interplay. Using the code, we can map out parameter spaces and see the predictions or the values of the cross section that you'd need to get in order to achieve the correct relic abundance given a certain population of primordial black holes. For example, entropy injections after freezing can dilute the dark matter distribution or dark matter abundance, and that requires a larger cross section. And so that's what we see here. We also see basically how black hole spins can affect your production of dark matter through freezing. And then with that, because I imagine I'm basically on time, we really see that we have like a complicated situation. There's more work to be done. But it's quite interesting because I think that this shows that there's really like a bright horizon of like interesting ideas and interesting work that can be done around something that's really dark and mysterious, which is the origin of dark matter, and you know that possibly primordial black holes in the early universe can play a role in the origin of dark matter, and yeah, so we developed this public tool. It's available for you all to play with now, and you can look at how the coupled Boltzmann's equations develop over the expansion of the universe. And we also saw, and we made assessments of situations where evaporated dark matter particles rethermalize, and that tells us that we have to do this again, but with a more careful treatment where we track the full phase space. And with that, I'm going to finish. So thanks a lot for listening.
Yeah, thanks a lot, Andrew, for this interesting talk and for the provision of the public tool, which is, I think, always a complicated but useful endeavor. Are there questions? Huang Yu, please go ahead.
Thanks for the nice talk. I just have one question, just curious. The lightest dark matter you show here is like 1 MeV, right?
Yeah.
So I'm just curious, will the story be significantly different if you consider much lighter dark matter particles like EV or even fuzzy dark matter?
Sorry, I just need to get. Yeah, so if you look here at this plot, we consider when we consider the like 10 MeV dark matter case, Maybe I didn't just like explain it as well as I could have, but these lines are kind of not the same color as the dark green here. They've been paled out. And actually, yeah, this is something the referee said to us. We can do this more, so in a way it's more clear. Basically, this is meant to signify that warm dark matter constraints from Lyman alpha forest tell you that your dark matter is going to be significantly boosted, and the expansion of the universe won't redshift it enough to make it cold in time for structure formation.
I see. So you're not allowed to produce such particles?
Yes, yeah, you produce them, but they would not be dark matter because they would have a really large free streaming.
Yes. Thanks.
Thanks for the question.
Okay. I don't see other raised hands. Then, Andrew, thanks again. And we come to our next speaker, which is actually Huang Yu.
Okay, thanks.
Huang Yu, can you, yes, and please try to show your slides.
Okay. Can you see my screen?
The screen, yes, perfect, full screen. Good,
okay,
simulation
great.
of axion mini halos. Please go ahead.
Okay, thanks. And thanks for organizing this nice conference. I've been really enjoying it. Today I'm going to talk about exactly the title of the simulation of axion mini halos. And this is a work collaborating with Ian Williams and Matt McQueen at the University of Washington. And first, I'm going to motivate the axion as an interesting dark matter candidate from the perspective of particle physics. So axion is a natural solution to the so-called strong CP problem. So why the CP symmetry is conserved in strong interactions? And to be more specific, actually, we have a great measure for this CP violation, the neutron electric dipole moment. So it's a direct measure to the CP violation term in the strong interaction. And we can think about this classically just because we have a better picture for that. So imagine you have a neutron model, you have up quark, down quark, down quark. And just remind you, the up quark has charge 2/3, down quark has a charge -1/3. And then you can compute, right, from this classical picture, you can compute the electric dipole moment. You just sum up the charge times the position. And generically, you would expect there will be some theta angle between these two lines. And we have measured this from the measure of the neutron electric dipole moment. We know this theta should be extremely small, should be smaller than 10⁻⁻10, which means you cannot have an arbitrary configuration like this. You should really have a configuration like that, which is mysterious in particle physics. Because, you know, supposedly from the theoretical point of view, this should be randomly distributed. And also, unlike the cosmological constant problem, we know cosmological constant is also small, but there is an anthropic solution for that. There is no anthropic solution for this theta angle. For example, if this theta is really small, but bigger than 10⁻⁻10, like 10⁻⁻3, our nuclear physics is almost the same with the current theory we have, and then everything is fine, galaxy formation is fine, BBN is fine, but then it's different from the experiment. So anthropic solution is not very likely. So it's mysterious. And axion is actually a good solution to that. We can just imagine this theta angle can be dynamical and it can change over time. Theta of 0, it's simply the ground state. And at the quantum level, we really have to think about this quantum mechanically, of course. At the quantum level, it's not helpful to think about the geometric angle anymore. However, you have a similar theta angle, which is a parameter and which is still a measurement for the CP violating term. And the axion solution, it's simply to promote this parameter to a dynamic field. And that dynamic field has some non-perturbative contribution from QCD. So it has a potential like 1 minus cosine theta. And as long as you have this potential, you know, if you start your theta value here, then naturally the rolling of field will cause that you will eventually go to this ground state, which is the state that has theta equal to 0. So during that process, you also create long relativistic axions, basically converting the potential energy to the energy in matter. So at the same time, you also produce dark matter. That's why axion, it's a very well-motivated dark matter candidate. It can solve a problem in our theory, and in the meantime, it can naturally give you the relic abundance. So that's why it's so interesting. Also, more than that, it's very detectable, perhaps, from the perspective of astrophysics. So when the symmetry breaking happens, you know, the vacuum takes different field values, I mean theta values, at different horizon patches. And here I'm just showing you different horizon patches, and different colors just represent different theta values. So if the symmetry breaking is after inflation, the field will not be homogenized. So you have different color at different horizon patches. And then you turn on the QCD contribution. You turn on the potential. Then the potential will convert the energy, you know, to the matter density. Then you have different matter density at different horizon patches. And then you have the axion perturbations. Then axion perturbations will form small-scale structures known as axion mini-clusters. And for the simulation, I will be talking about the detectability of those small objects. And why it's so interesting recently for the study of axion mini-clusters, because we have a lot of new ideas of detecting small-scale structures. By small, I mean really small. So we have microlensing. Microlensing is only sensitive to highly concentrated objects. And we also have pulsar timing arrays, which could be sensitive to mass from 10 to the minus 12, which is really small, to all the way to 100 solar masses. And this has been discussed by Catherine Zurich's group. And also we have lensing in highly magnified stars, which is discussed in this paper. And so we have a lot of interesting probes. They're mostly in the near future. And it's interesting to study the physics, especially the dark matter physics, the interesting dark matter candidate axion that can lead to the formation of those objects. And then perhaps we can detect or rule out this axion scenario. Okay, some fun facts about the axion mini-clusters. We have talked about you naturally have that axion mini-clusters formation because of at different horizon patches you have different field values. So what is the exact characteristic mass you expect from this process? It's actually very simple. If you consider QCD axion, the conmoving Hubble sites at that time, the conmoving Hubble will tell you the kind of the size of the axion mini-cluster, and that will be corresponding to a characteristic mass, which is about 10 to the minus 10 solar mass. So this is really small. And this is probably the smallest. Our conference title is from the largest scale to the smallest scale. This is probably the smallest scale we have today. So this will lead to the formation of small scale structures at matter radiation equality, known as axion mini-clusters. And we will call it axion mini-halos at later times because they will merge and form bigger structures. And that's just give you some idea about how small this could be. Now, we have some natural questions for that. How do those objects evolve with time and how compact they are? This will be crucial for the detectability. And also from another perspective, are there still axion particles that remain unbound? This would be important for the direct detection because for the direct detection, they have assumed all the dark matter particles are free particles. But if they have been bound into like objects like axion mini-clusters, this may reduce their signal. So this is the first time we use n-body simulations to directly study the detectability of axion mini clusters and axion mini halos. And this is the simulation setup. So as we know, QCD axions have different field values at different horizon patches, and this would result in a white noise Power spectrum. Because you simply have different field values, and then if you look from a large scale, this will be averaged out, so you have less inhomogeneity. But if you look at small scales, they have a very large inhomogeneity because of the difference between different horizon patches. So this is really just white noise. So we can initialize the perturbations with the white noise Power spectrum and run it with the MP gadget. And we took our simulation box size to be 50 parsec divided by liter H, and the particle numbers is 1024 cubed. So we run the simulation all the way from radiation error, like 30,000, all the way to redshift 19. So this is the lowest redshift so far in the literature of simulating axion mini halos. And I will show later why redshift about 19 is sufficient to determine the detectability of axion mini halos. So just give you some picture about the evolution of structures, and I took 2 snapshots from my simulation. This is at redshift 99. It's a selection box of a simulation, and you can see from the perturbations, it's pretty much like white noise. You're not seeing noticeable structures. And then if you go all the way to redshift 24, you can see, okay, there are larger inhomogeneity from the delta rho, and you kind of see a lot of structures. So this is just confirming that you would evolve this white noise Power spectrum to some interesting small scale structures. And also, I can just identify the halos in our simulation and compute the mass function of our axion mini halos. So the data points are simply the mass function from our simulation data. We also, and the solid curves, very interestingly, it's a tweaked Chateauman model. We simply tweaked the Chateauman parameters to fit our simulation results, to fit the mass function at different redshifts. And the data with the smiling points, smiling faces, are just from simulation without a cutoff in Power spectrum. So we kind of have 2 simulations. One is a simulation with white noise Power spectrum, but has a cutoff at a certain scale. And that cutoff is motivated by your horizon patch again. So you have inhomogeneity outside the horizon. But then if you study inside the horizon, the sub-horizon inhomogeneity, we have assumed the field value is constant, so you would expect a cutoff. And that cutoff will be corresponding to a break. So you would expect less structures for a certain mass. And to confirm that break is due to the cutoff, we run another simulation in comparison to the white noise Power spectrum without cutoff. So this is simply confirming that. However, this cutoff is not crucial for our result, for the detectability, I mean, because as you can see, I'm plotting m times dn d log m, which is more like the mass fraction, the mass fraction d log n. So you can see dominantly, your axion have most of the mass at this region. For redshift 99, it's here and moving to larger masses because they are constantly merging with each other. So you can see for redshift 20, the preferred axion mean halo mass will be something like 10 to the minus 7. And that will be important to determine the detectability, because you have to directly compare this to observers like pulsar timing arrays and microlensing in highly magnified stars. So, but however, as I mentioned before, I stopped the simulation at redshift 19. To be honest, it's because if you run further forward, it's very hard. It's numerically very expensive. And also from physical point of view, that's enough because you cannot trust your mass function anymore if you go beyond the ratio 20. The mass function cannot be trusted anymore simply because the large scale structures will start to form. And you know, our simulation box is really small. It's just 50%. And it knows nothing about our large scale structure. It only knows this small box. And you should always include the large scale structure effect once they form. And it's impossible to do that because the dynamic range is just insane. So we have to be smart. We compute the current mass function, which is this purple curve, by including those incorporated, by including those mini halos incorporated into the massive CDM halos. Basically, the assumption is that once the axion mini halos fall into CDM halos, they stop merging, they stop the evolution. It's a mass function is frozen, excuse me, at the exact moment it falls into CDM halos. And then you can compute the mass function.
Sorry, you have about 2 minutes left.
Okay, thanks. Yeah. And then to further determine the detectability, you also need the density profiles. And we have found that the density profiles, it can be well reproduced by the NFW profile. And you see there are some anomalies here for the high mass end of the halos. So that's mainly due to the substructure. And probably I don't have time to show that. And we have found a nice mass concentration relation like this, which has been parameterized with the characteristic mass of our axial mini halo. So this is given by this solid curve. And this mass concentration relation has some analytic motivation. So it fits well with our simulation. And then we can directly compare this with the detectors. So basically, this is our mass function with different axial mass. And this is the final mass function. And the band here is the required abundance to give PTA signals, the pulsar timing arrays. And the abundance here is the minimal abundance to have Nancy with magnifying stars. So you can see they are broadly above those thresholds and they can be detectable in the near future. And that will be super interesting because there are very few physics that can lead to structure formation at such small scale, 10 to the minus 10 to 10 to the minus 6. And we do have observers for that. And if it's detected, it's going to be super interesting for our dark matter physics. And the conclusion is that we run a simulation. It can be well described by tweaked Schattauman model. Density profiles agree with NFW, and future observations can test this scenario. Maybe either rule out or confirm that either way would be super interesting. Thanks. That's my talk.
Thanks a lot for this interesting and I would say different talk, at least for me. This was very nice. I see several questions. Let's start with Caitlin.
Hey, great talk. I was just curious because I know some other groups have done similar kinds of simulations for axion mini clusters and mini halos. And I think some other groups were doing things earlier in the universe, and there was some disagreement about how to treat cosmic strings when you have these different values of the theta parameter between different spatial regions coming together and forming domain walls and cosmic strings and giving you more contributions to the axion density. I'm just wondering if that's something that you had to take into account in your simulation, because I know different groups were finding pretty stark differences between whether they were including those or not.
Okay, great. Thanks for the question. It's really important. So I haven't time to go through this very carefully. So you can see here, I'm assuming different axial masses, and this mass is simply motivated by the misalignment mechanism to produce the relic abundance. And this 500 mass is actually motivated by, the string production for the axions. So I did take this into account that if you have string decay dominating the axion production, then you have different mass. And I'm showing and because I'm using a white noise pulse spectrum and it's scale invariant, so our model can apply to arbitrary mass. So I took that into account, so it could be applied. So whatever result they got, our model can be applied to that specific mass. So then you can study the detectability for that. That's part of the answer. And the other answer, they also studied the domain walls and string decays, those different topological objects, which may give you different pulse spectrum, especially the pulse spectrum at the UV side for smaller scales. And I'm claiming that the UV, which will affect the population here. So I'm showing one with cutoff, one without cutoff. And if you have axon strings as topological objects, like it's exactly the topological objects inside the horizon, then maybe you will have more population here. So that's exactly the case. And I'm claiming this is not super important for the detectability because most of your mass will be at this end. So it will be at the high mass end and it will be more Gaussian. So if it's from string decay, there will be non-Gaussian perturbations. But if your most of the mass are from the merger of those mini clusters, it will be more Gaussian and you care more about the high mass end. And from the perspective of detectability, their results will only change the preferred mass range of this axon mini cluster. And our model can still apply if you are interested in the detectability or not. Does that answer your question?
Yeah, great. Thank you so much.
Yeah.
Okay, one more quick question from Shema.
Hi, thank you. Very interesting and very nice talk. So my question is related to this possibility of using microlensing of distance.
Yeah.
And I am concerned it's maybe quite more challenging than previously thought, because you have to compete with other microlenses that are going to be equally abundant, if not more, depending on where the magnified star is. It's going to be near, of course, for sure. And in particular stars or even other planets or other bodies of variable mass. So has there been any thought about how complicated this will be in a realistic?
Yes, I think in this paper they have spent a lot of they have put a lot of efforts to study the detectability of axion mini halos in highly magnified stars. So I agree, they might be degenerate, as you said, with other planets, especially those free planets. But basically, you kind of know the population of those planets. And we are talking about dark matter here. We have much more dark matter than baryonic matter, as we know. And we are interested in this mini halo. And if you do have if you do have a white noise pulse spectrum, and then you would expect about 80% of your dark matter will be bound in those axial mini halos. So this will be a lot more mass than you have in planets. So I think then it will be definitely more detectable than those planets. So you would expect a lot more objects.
Thanks.
Does that answer your question?
Partially, yes. Thank you.
Okay, yeah. Thanks.
Okay, thanks a lot. Thanks again, Huang Yu, for this interesting talk. And we come to our last talk, but not the last part of the workshop, because this will be the roundtable after the last talk. We have Bartosz. Yeah, I see your slides already. Full screen.
And you can probably hear me.
Yes, we can hear you well. Please go ahead.
Thank you very much. It's a real great pleasure to be here, and I'm really grateful to the organizers for having me. So I do realize it's the last talk of the workshop, so I'll promise to be brief and straight to the point. So we heard fantastic talks during the workshop about different ways of approaching the dark matter problem through accelerators, direct detection experiments, indirect signatures involving photons and other particles. So here I'm going to talk about the other possible avenue of investigation, which actually concerns gravitational waves. And it's a very, very long shot, but perhaps in the future with some improvements, it'll turn out to be more fruitful than it currently is. So this was done in collaboration with a postdoc at the University of Utah, Barmak Shams. So I will base this on an example on a simple model. It doesn't have to be applied to this particular model, but just to focus our attention on something. So we know very well that the standard model is based on the gauge group SU3 color cross SU2 weak cross U1 hypercharge. But apart from this gauge local symmetry, it also exhibits accidental global symmetry, namely baryon and lepton number. And since global symmetries are not really pleasant to quantum gravity, one usually looks for a way out. And a possible way out is to promote them to the status of gauge symmetries themselves. So this has been tried on very early on in the 70s. And there were models constructed with gauge baryon lepton number in the 80s and 90s. But the first kind of modern model, which is consistent with all observation, was constructed just a decade ago by Mark Weiss and Pavel Filebius-Perez, and was followed up by other models of this type. So here, just an example to show the capabilities that gravitational waves are providing us. I'll just focus on this first model by Mark, Pavel, and Michael. So briefly, what is the model? As I said, the details are not that important. So the standard model symmetry is extended by a gauge baryon and gauge lepton number, both U1 gauge symmetries. Of course, this introduces extra anomalies in the theory, and they are canceled by adding extra fermions. So there's 3 generations of right-handed neutrinos are added, plus those particles over here. So the first 3 numbers are the standard model quantum numbers, and then each of them carries baryon and lepton number. And so you see the last particle, the chi right and chi left here, it's a standard model singlet under color, weak charge, and has 0 hypercharge. So a priori, this signalizes this might be a good dark matter candidate, but we have to, of course, check that. And in order for the anomalies to cancel, there have to be some relations fulfilled between those quantum numbers. So of course, those symmetries cannot be gauge symmetries to the very low energies. They have to be broken at some scale. And this is achieved by introducing the scalar field, which breaks lepton number phi L, carries lepton number 2, and baryon number is broken by the VAF of this phi B, which carries both baryon and lepton number -3. And they are both standard model singlets. So in this model, there's a natural separation of scales if we want to have the neutrino seesaw mechanism implemented and a dark matter candidate. So the VAF of the field breaking the lepton number is at a high scale, because if it's at a high scale, it can produce a large right-handed neutrino mass term and lead to a successful type 1 seesaw mechanism if this VAF is at 10 to the 11 GeV. Of course, they have to be both larger than the Higgs, but it turns out there's also an upper bound on the breaking of baryon number, which causes those 2 scales to be quite separated. And before I get there, just mention one thing. Since this field breaking baryon number carries baryon number 3, it can only break B by 3 units. So there's absolutely no proton decay in this model, even at the non-perturbative level. So surprisingly, after breaking of U1 lepton, U1 baryon number, there's a residual symmetry under which only the new fields transform, the fields carrying baryon lepton number. So the lightest of them will remain stable. And if it happens to be a standard model singlet, it automatically turns into a good dark matter candidate. And so assuming that indeed the chi I mentioned earlier is the lightest of the fields, then it's automatically a candidate for dark matter. Within this model, there's also an annihilation channel for free, which leads to actually the correct relic density. And that is what imposes an upper bound on the scale of breaking of baryon number. Because if you want to have the right relic density and also keep all the couplings perturbative, it turns out that the highest scale of B breaking is approximately 20 TeV. Of course, it can be lower, in which case, great, this can be searched for at the LHC. But if this scale is around 20 TeV, then LHC unfortunately cannot probe this. So there are 2 things we can do: either sit down, relax, and wait for the future 100 TeV collider, or do something about this. This something can be using gravitational waves to say something about this regional parameter space. So how does it work? Well, it turns out the gravitational waves are emitted. I'm not talking about the gravitational waves coming from the mergers of black holes and neutron stars. I'm talking about the stochastic gravitational background, which was emitted in the very early universe. And there are two ways that a spontaneously broken Yuan gauge symmetry can lead to gravitational waves production. First is through the production of cosmic strings, which is a long-term process. And the dynamics of this network of cosmic strings causes gravitational waves to be emitted. And the second possibility is through a first-order phase transition, which happens on a very short time scale at the very early universe. So about cosmic strings, what are they? Well, they are topological defects in one-dimensional field configurations where the symmetry remains unbroken. And they are characterized as by one parameter, the string tension, which is directly related to the scale of the symmetry breaking. So this part is a little model independent, well, very model independent, since the string tension depends only on the VEF, not on the details of the model. So they yield a pretty model independent signature, which depends only on the VEF of this U1 breaking. And there are two competing contributions to this such a string network. Namely, first is stretching due to the expansion of the universe. And then also when two or more strings intersect, a piece can be cut off. And then this little piece is a string loop, which oscillates and decays via gravitational radiation. So this competition between those two, the stretching and the formation of string loops, which radiate, leads to the so-called scaling regime, where we have a small number of really big Hubble size cosmic strings and a large number of string loops, which are constantly being produced and decay. And this actually leads to a flat signature from gravitational wave. So this is how it looks like. This is the expected signature in this model, or actually just depends on the, essentially on the VEF only. On the horizontal vertical axis, we have the strength of the gravitational wave signal. And the x-axis, we have the frequency of the gravitational wave. Both are on a log scale. And this black line here corresponds to exactly our case, where we assume that the breaking of lepton number is at 10 to the 11 GeV. For now, this is below the sensitivity of LIGO, but upcoming experiments will be able to see such a signature if it really exists. Now, the other way gravitational waves are produced are, as I mentioned, through first-order phase transitions. Of course, you know, the effective potential has a tree-level part, but also a one-loop Coleman-Weinberg correction and a finite temperature correction. So as the temperature goes at high temperature, we live, of course, the universe is in this highly symmetric state. But as the temperature goes down, a new vacuum can form, and which can be actually a true vacuum, can be lower than the previous one. And the universe can actually tunnel to this vacuum with lower energy density. So what it corresponds to is that different patches of the universe can undergo such a first-order phase transition. And in each of those patches, a bubble is formed and starts expanding. And of course, bubbles can interact with each other, can collide, sound waves are produced, there's turbulence, and all those processes lead to unique gravitational wave signatures from this first order phase transition expected to be seen today. There are only 4 parameters which describe such a signature. One is the bubble wall velocity, which is usually a model input. The temperature at which bubbles can effectively start nucleating, the duration of the phase transition, which depends on this function S here. This is the Euclidean action, which corresponds to the bound solution interpolating between the false and the true vacuum. And finally, there's a strength of the first order phase transition, which depends on what is the energy density difference between the two vacua. So with this input, one can run simulations, and they lead to an empirical formula for the gravitational wave signature, which is given right here. It just depends on those four parameters. So usually what one expects Here is, again, the plot of the strength of the gravitational wave signal as a function of frequency. One expects a structure like this, essentially a bump. And in most cases, the leading order contribution comes from sound waves. So how does it look in our case? In this case, we fortunately have two vastly separated scales, one at the U1L breaking at the high scale and U1B breaking at the low scale. So this is how it looks like for a particular parameter choice in our case. This is, again, the strength of the gravitational wave signal as a function of the frequency. And the black line shows the expected signal from this model for a particular parameter choice. The flat part over here and here comes from cosmic strings. And the bump here results from the first order phase transition, and which happened around the scale of 20 TeV. And the breaking of lepton number was assumed to be at 10 to the 11 GeV to have a successful neutrino seesaw mechanism. Overplotted are the sensitivities of future experiments. So LIGO, unfortunately, is the sensitivity is still too low. It would be somewhere over here. But we can see the future spacecraft LISA over here, the SIGO, Big Bang Observer here in purple, Einstein Telescope, and Cosmic Explorer. Hopefully, all will happen within the next this century. Well, it'll happen within the next few decades for sure. So you can ask a question: well, can we have anything, any relevant information about the dark matter itself from such a signal? Well, unfortunately, it's not that bright, right? The dark matter mass enters the effective potential, both in the Coleman-Weinberg and the finite temperature part, through its Yukawa. But there are other parameters in the model. So there is dependence on the dark matter mass in this signature, but it's buried under a whole other, with several other parameters. So at this point, as I said in the very beginning, it's a very long shot. It's hard to extract any useful information about dark matter itself, but at least we would have a clue that there might be two different symmetries broken at a vastly different scales. You might ask, well, how generic is such a signature in this particular model? So here's a plot showing the gauge coupling for baryon number and the quartic coupling. And the colored regions are what can be what the upcoming experiments will be sensitive to. So LISA here, the SIGO, and Big Bang Observer. So of course, it won't probe the entire parameter space region of the model, but at least some regions it'll be sensitive to. So as I said, hopefully there will be some more progress made in the coming years so we can extract more valuable information about dark matter itself. So let me end by saying
you have 2 minutes.
Okay, great. Okay. We have been trying to attack the dark matter problem for 50 years in accelerators, direct detection experiments, indirect detection signals. So hopefully the gravitational waves will help us to corner it and finally force dark matter to reveal to us its real nature. So thank you very much.
Thanks a lot for this interesting talk and these different perspectives on the detection of dark matter. Are there questions? There should be 2 raised hands, but I do not see them. Okay, Andrew, please.
Hey, thanks for the nice talk. I just, could you comment on like whether this model can give you baryogenesis in the universe or?
Oh, this particular model here? It has been, I'm not sure if it was explored in great detail. Mm-hmm. So definitely if you assume, sorry, so we are over here. Yeah, if you assume some sort of asymmetry at the very beginning, it kind of enables you to keep it there or transfer between the dark sector and the, so it kind of has a possibility of having something like asymmetric dark matter. but you have to assume the asymmetry at the beginning. So it doesn't let you generate it for free because barrier number is a gauge symmetry. So it's hard to get that to work.
Okay, thanks.
Okay, we have one more question, Spavaska.
Hi, I wanted to know whether you can get any signatures of dark matter from cosmic strings.
Well, in this case, the strings are produced from the U1 breaking, so they don't really care about whether there is a dark matter in the model or not.
Okay.
There might be implications on. You're right. There might be some implications of how the signal propagates to us. So maybe the dark matter modifies the expected signal in some way.
Okay.
But I haven't investigated this. We haven't investigated in this case such a scenario.
Okay, thanks. One more thing is when you say the closed cosmic strings, the decay, you mean by they emit gravitons, right?
Yeah, they emit the gravitational waves. Yeah.
Oh, okay. Thank you. Yeah.
I don't see any other raised hand, but I have a question. Can you go to this final plot where you showed Lisa, BBO, etc.? Yeah. I mean, normally when one sees this kind of plot, and then one looks at the signal over noise ratio, and this is then an integral over the ratio of these two curves and integrated over the frequency range. But given you must have a huge signal over noise ratio here, it must be fantastic.
Of course, yeah. In this case, even a small overlap would yield more than a 5 sigma discovery, right?
Yes, but could you even kind of try to really map the frequency spectrum, or this is possible, or?
I mean, map like for different parameters, you mean?
Maybe I'm not sufficiently familiar with this, but usually I think one says we see a signal or not, but would you really be able to see kind of independent signals for small frequency ranges? And
you can integrate the data right in every range. I'm not sure what the sensitivity will be.
Would be integral over a small frequency range, and then one could maybe even kind of map out this curve.
Exactly. Yes. Yeah. So you'll have information about small frequency ranges, so you can essentially, if there's a signal like this, you will see this bump. Yeah.
Yeah, this would be great. Okay, thanks a lot. Really interesting. Good.
Thanks.
No more raised hands. Thanks again. This concludes the talks of the Dark Matter 2021. But as I said before, we have the round table discussion. And please, our 4 round table participants, show yourself if possible. Yeah. Okay. 2 already. So we have Keith Olive, Joe Silk. Yes, we have Simone Murgia. Well, no, I'm not sure whether I pronounced the family name correctly.
It's fine.
It's fine. Okay, thanks. And Tim Tate should also be here. I saw him already connected.
I am, yeah.
Okay, very good. So I don't think I have to say who you are. You're all well-known experts on various aspects of dark matter. Well, I think actually most of you have institutions in the US. Yeah, only Joe has an institution in Paris as well. But I understand that Joe prepared a couple of slides with topics that you consider as relevant or interesting, and then you will say something about it. And I hope that also some questions from the audience will come up. So, Joe, please go ahead.
Sure. Let me see if I can share my screen.
Before it worked out perfectly.
Yeah, anyway, I just wanted to, actually, I was going to comment on one particular topic, actually, which is the question of whether dwarf galaxies can be considered to be a source of anomalies that motivate dark matter models. So that's really what I want to talk about. And let me...
let's try to go for the slides.
Okay. Let's see, can you see the slides, perhaps? Okay, is there anything there or not? Sorry, I don't think I shared my screen.
No. Now this looks better. Very good. Please go ahead.
Good. Okay, great. Okay, so I just want to focus on this topic because, it's been a source of, intense discussion over a decade as to whether we need certain types of dark matter to help explain certain anomalies. We heard actually two wonderful talks on this, just by Caitlin and Farah. And what I want to say is partly going to just summarize their points of view, actually, with maybe one ingredient about the remaining anomaly, which I think is a worry. So first of all, I just wanted to remind people that simulations have been amazingly productive because they seem to give us a way of reproducing complex structures in the universe, the galaxies. So here are a couple of examples where you see a real galaxy compared to a simulated galaxy in different simulations. And at first sight, I don't think, apart from the details of what we know and what we don't know, you can't tell that the simulated ones are not even real galaxies. But of course, there is a question here. When simulations are this good, do we actually have to believe them? And so this comes up especially when we study dwarf galaxies, where the structures are really puzzling to us in the sense that we have a very hard time reconciling their properties with the simple predictions. And part of the story is that we simply don't have the physics in these simulations on the wide range of scales you need to cover this. Anyway, so that was just a very general remark. But now let me just summarize the several different ways that these anomalies have arisen. So the first one, of course, is just the numbers of the dwarfs. The simple cold dark models predict vast numbers of small objects, and above a certain mass scale, roughly dark halos of 1 million solar masses. These are certainly popular with baryons that could cool and make stars. But the new result, as I just summarized, is that when you put in the observational selection effects for these very, very thin galaxies, I think there no longer is much of an issue. You can't really distinguish the different models from each other anymore. Maybe when we go to really, really faint galaxies in the future, this may change slightly. But anyway, that's where we sort of, I think, stuck at the moment. It's not, the exotic models have not really, more exotic models than cold dark matter have not really solved an outstanding problem, I would say, is the bottom line there. The other issue that has plagued people for a long time is the question that in the simulations, dark matter halos form with roughly 1 radius profile, 1 profile cusps and FW cusps, and these simply are not seen in the data. Well, very few are seen, but by and large, we find dwarf galaxies, which are, of course, wonderful dark matter laboratories to have cores rather than cusps. So that's an issue, but it turns out that when you do the modeling more carefully, and one example is simply you no longer assume simple isotropic velocity profiles, but have more realistic ones. And that, of course, gives you a possible, if losses are anisotropic, for example, the cores, then you can be underestimating or overestimating the density, depending on how you model it. And it turns out that when you do more correct modeling, that you can fit the data with the cores, possibly cusps too, but the better models seem to give you a range, which is more or less what we see. So that is, I think, a statement that in the data you can't do very much. And then, as you heard already in the theory, if you have a simple NFW, dark matter only profile, you of course do get the cusps. But once you put in the complex physics of baryonic feedback, star formation, supernovae, whatever, moving the gas around, then this effectively heats up the dark matter dynamically. So that's one, I think, another issue that's been laid to rest pretty much. Another one is the question of the radial gradients in dwarf galaxies with respect to their host galaxy. And again, this is another interesting fact that the early models said that there was a real issue, that they should be far more in the inner regions than the outer regions. And again, what we've found as you put in more realistic physics of the environment, disrupting the dwarfs, etc., is that the data fit beautifully. So there is, again, no particular issue there. The last of the classical ones, I would say, that we think we've solved is the whole question of diversity. Again, the complexity of baryonic physics, and you saw this slide already in Farah's talk, is that one can basically have a huge variety in the dark matter content, for example, which is what you see, which you would not expect in the simplest models. So there's one issue which I just want to mention finally, which is outstanding and has not been solved. And maybe this is the ultimate dwarf frontier. And so this is the one that's been called the vast plain of satellites. So you have around our Milky Way, the best studied one, but also a couple of other galaxies, including our neighbor Andromeda, the fact, observationally, that many of the smaller satellites are in a flattened, elongated plane. You can measure the size of the plane roughly, the velocity dispersion, etc. So where does this come from? This is not simply predicted by the standard model. Okay, and again, I think we don't quite have the answer to this yet. It would be a major issue, I think, for our understanding of dwarf galaxies. But there is something intriguing from the latest data, which is that when you look at the dwarf galaxies in our Milky Way, the best studied vast plane, relative to the Large Magellanic Cloud, there is this clear indication that some of those dwarfs came in when there was a merger long ago with our nearest neighbor, the Large Magellanic Cloud. And this leads to a rethinking of the probability of finding dwarfs. So this shows you, roughly speaking, that the probability of, if you don't include the Large Magellanic Cloud simulations, you have a 2% chance of finding these vast planes, which is a worrying thing. But once you do the dynamics with more of this environmental physics in hand, then the numbers go up to of order 10%, which is maybe not something to worry about. And if in addition you realize that our own galaxy had some complex merging structure too, that might also have played a role in the alignment, I would say that the jury really is out on this question completely, or whether the vast plane of satellites is a problem. So I think finally, I would say that the popular dark matter models are certainly constrained from all of these things. There are many, many papers on this now. But finally, the bottom line is that what worries me most is that Einstein had really strong motivation when he invented general relativity. He found an anomaly that motivated him. And this was certainly a very strong hint of new physics. But that anomaly had been studied for hundreds of years and was a very strong and rigorous anomaly in the perihelion of Mercury's advance. I don't think dwarf galaxies meet this threshold for any new paragraph. And also just looking at the data and the theory, the anomalies are disappearing as we get better physics and better data. So I think summary is dwarfs are a great way to test dark matter models in principle, except so far the real universe is just too complex to make this a very effective test. That really was the remarks I wanted to make.
Yeah, Joe, thanks for bringing up again this really important and interesting topic. And of course, I guess we all would like to hear the opinion of our other three members of the round table. Do you agree, or do you think that there actually is a problem and we should find a new way to describe the dwarf galaxies?
Well, I think the physicists, the simulators, definitely need to refine the physics more and more, and they're doing exactly that. So for the moment, I think, let's move on.
Yes.
Well, I can comment. I agree wholeheartedly with that. You've got the situation where you have observations, which, as Joe mentioned, they also have a little bit of their limitations due to bias. And in some cases, you can correct for that. And then you're comparing them to simulations, which is, you can say that's comparing to theory, but it's not really comparing to theory. It's comparing to a model of theory, which is much more difficult than writing down something like simply cold dark matter or lambda CDM. And so when you get these kind of anomalies, what you're really learning, not necessarily, I mean, a priori you don't know, but in this case, what you're really learning is that there are deficiencies in the model, in the simulations. And okay, and then you work to improve those simulations, and then you see that the anomalies go away. You end up then with a better understanding of the model and how to do your simulations, but you don't get any new fundamental physics in terms of you're not really learning, oh, now we know what the dark matter candidate is. You can push that farther now and compare that with other experiments, and now the difficulty becomes sort of amplified because we have such a lack of experimental data that's telling us something definitive beyond the standard model. I mean, we know that the standard model is not complete. And whether that's dark matter or something else that you need to put into the standard model to get a full picture of the universe, what that is not being shown to us, right? We have some little anomalies, in accelerator experiments. We have this G-2 anomaly. Okay, does that have anything? Do any of these things have to do with dark matter? We don't know. There is the temptation that no matter what the anomaly is in physics, that its solution is always dark matter. And I would caution that there's really no reason for that to be the case. It might be, but it's not necessarily. And so whether or not the solution to G-2, whether it's beyond the standard model physics, or whether it's a problem in the calculation, or both, it may or may not have to do with dark matter. And so my worry, I think, is going forward is how are we going to know what the dark matter is? How are we going to experimentally determine it? A lot of our models for dark matter are giving extremely low detection rates. And, does that push it out of the realm of physics to metaphysics? I don't know. We know that there should be dark matter, but how we're going to determine it, whether it's through direct detection, through accelerator experiments, or indirect detection, and really test the theory and push the theory in a new direction is going to be very difficult. And so that's my chief concern.
Yeah, I would just add that we have to be lucky, really. I mean, maybe we will have a gamma ray signal from the galactic center. We need and then that could lead to multi-messenger signals. And then I think that would be very convincing, but we're just not there yet.
Yeah, I think luck is a big thing.
What do our other two roundtable participants think about this, please?
Okay, maybe I can pitch in a little bit. I definitely agree with Joe and Keith. And one of the things that are pretty obvious is that we need to understand the conventional astrophysics better. In the case of the simulations, we need to, make sure that things are done in a way that is representative of what the universe is like. In the case of indirect detection, and Joe mentioned the galactic center axis, well, we do have a booming signal from the sky It's pretty bright, it's there, but we don't know what it is, and we really need to understand the conventional astrophysics there. The problem is that it's hard. It takes time, and we don't really have at this point, and now I'm talking specifically about the galactic center accessing gamma rays, we don't really need, we don't really have all the tools that we need to sort it out at this point, and this is my opinion. I think Rebecca Eileen had a very nice talk where she covered a lot of grounds on where the difficulties are in interpreting that kind of signal, astrophysical signal. And yeah, I mean, we really need to understand the backgrounds better, or maybe ideally, that would be my preference, have even better instruments to see this signal better, but that's the whole different set of worries. Yeah, we do need to be lucky in a way, certainly that's the case. But sometimes I think when it comes to indirect detection, one thing that I feel is important and maybe has been neglected a little bit is to build an experiment that's actually going to do that kind of physics well, instead of being an add-on to a mission that was designed to do other things. And in case of the galactic center access, well, what I think will be really helpful is a new instrument that has a much better angular resolution. So you really those sources of gamma rays, so you'll know where those gamma rays are coming from. So yeah.
Okay, Tim, what do you think about it?
Yeah, no, I think that we've heard a lot of really good thoughts already. Certainly, I think if you look at the slides that Joe presented, and I agree very much with actually the way that Keith reacted to them. What it really highlights is the fact that what we need is more. We need more and better observations. We need more and better simulations, right? We need to keep working on them. And it's clear that the stakes are very high because we can learn about the fundamental properties of dark matter if we're lucky and if we have the tools. And it's very interesting to see how, particularly in the morphology of dwarf galaxies and their distribution, how that's really been a really nice story to live through in the last decade or so, where you see things in the data that you don't understand, and then you see better treatment, more fundamental treatment of the simulations that actually make the predictions. And then you see that you start to actually understand some of the features that you're seeing in the data that way. And from that point of view, I think, it's a really fascinating, illustration of how science works. It basically takes theory and experiment and observation all coming together in a way that makes you move forward. Now, I mean, in terms of the bigger picture of looking for dark matter and looking for indirect detection, I think the same principle applies, and that's essentially what Simona just said, was that we really need more. We need more observations, we need better data, we need a better understanding of the backgrounds. Of course, if we had some way of coming at the signal, meaning some observation somewhere else that would help tie it down, that would also help a lot. But, I guess I get more philosophical at this point in my career, and I'm more, I used to be really aimed at the next discovery and wanting to see it. And, it may be that G-2 is that, and that we just haven't quite appreciated it, or it may turn out that it's really just, the nth decimal place in the lattice calculation hasn't been simulated properly. And that's also a possibility. But I think that the process of science is really going very strong here. And so the message I take away is that we're all doing the right thing, right, in terms of trying to struggle towards the answer. And again, I hope that we are lucky in the sense that Keith mentioned, and that we actually get to see what the answer is sometime pretty soon.
I think when you say we're all doing the right thing, I think globally that's probably true, not maybe locally. There's the principle of simplicity, and that's it's pretty weak principle, but that's what you try with. And I think the simulations are a good example, because what did they do? The earliest simulations did the simplest thing that they can do, right? Why start messing around? Let's just do the simplest thing, put in the minimal amount of physics that you think you might need, you get a result, okay? And now you find, oh, you do the observations and they don't agree. So, and then of course, all hell breaks loose and people start inventing all sorts of new particles, new forces, new this, new that. And you find, well, wait a second. No, we just need to put more physics in the simulations. And then we learn. I mean, it's not a vacuous exercise. It's quite useful. But the same thing then goes on the particle side. You know, why isn't the standard model U1 cubed? Well, that would be simpler, right? That would be a whole lot simpler if it was U1 cubed. But then you do some experiments and, well, and you find, well, U1 cubed doesn't work. And so you make it a little bit more complicated. And you end up with SU3 cross SU2 cross U1. You say, okay, that works. And now what do you have to do? Well, now you need to put in something more because you have dark matter. You have somewhere probably baryon number violation or lepton number violation in there. So you have to put in something more. And now the question becomes, you know, how do you maintain some degree of simplicity? I mean, how many parameters do you want to add to explain one number, right? One observation, you know, if you add enough parameters, you can explain anything, right? So I think simplicity is still an important principle to make sure that you are trying, you know, not overkilling a problem, because whatever anomaly or observation you see, you can fit it by adding a complicated enough theory, but I don't know that you learn anything that way.
So one other remark, though, certainly in the dwarf galaxy case, it's not just the simulations that we've refined greatly, it's also the way we treat the data. I mean, There's been this huge issue of systematics, et cetera, which
absolutely.
We're tackling, and that's a major part of the change in view too. Maybe that's going to be true for G-2 as well. I don't know, that we haven't fully understood what's going on there, or do you think that's a...
Well, the experimental side is probably not going to change, I think. You know, the fact that it
pretty
was
fair.
Huh? I mean, the fact that it was repeated now.
I'm agreeing. It's not going to change. It doesn't seem very likely.
Yeah, so the theory might change, but I think the experimental result, it's probably, that's the number, right? That's probably, you know, we'll get more data, you know, they'll eventually release their run 2. And, you know, I suspect, you know, if you were going to bet that, you know, it would move around maybe a tiny bit, but within 1 sigma, but the error bar will go down, which is just what you expect, you know, a good experiment to do. Does that mean we're even more sure there's an anomaly? No, not necessarily, because you have the theory side, and there's the systematics really on the theory side.
It's also worth mentioning in that context that the theory errors are not Gaussianly distributed, right? They're not based on statistics. And so we have to be really cautious when we interpret them.
I would also like to encourage the audience, if they want to comment something on the questions that were brought up, you can do this, of course. Yeah, you can ask the round table, or you can maybe contradict to something what they have said, because they all four seem to agree pretty much. We also have another set of slides, I was told, with another idea of question that could be discussed. Okay. I hope the audience is enjoying it as much as I'm doing it. I find it very interesting. Any one of the four of you wants to add to what has been said? Or you all think, yeah, in principle, Lambda CDM is still in pretty good shape and we just have to do our job better?
Well, I think it's in great shape. I mean, it's given, again, go back to simplicity, given the relative simplicity of Lambda CDM, the number of parameters that you're adding and the number of observations that you're fitting. I mean, you know, just look at the power spectrum, you know, the anisotropy power spectrum. I mean, it's unbelievable almost, right? That you can do that. Now, of course, there's going to, you know, at L equals to 20, there's something off. Okay. And I don't know what that is, but I wouldn't throw out the whole theory because of, you know, a deficit at L equals to 20. Oops, you're muted, Sven. You're muted. Sven, you're muted.
Yes, thanks. There's less controversy than I had expected, but if four experts from different subfields agree, it's also an interesting observation. Tim had told me that he also had prepared a couple of slides. Maybe you can start showing them.
Great, thanks, Sven. I did want to make sure the audience had a chance to jump in on this topic because I think it's really
the audience
interesting
can
and
always
important.
raise their hands. I'm trying to monitor this, but so far not.
Okay, no worries. So yeah, I also prepared a couple of slides, and I'm actually not going to even go through them in detail. I just wanted to illustrate one thing that I find very interesting lately, and that is that the production of dark matter in the early universe is an opportunity. We're used to thinking about it as an opportunity to discover dark matter or to understand it or to maybe constrain its properties, but that's actually not what I'm getting at. What I'm getting at is a theme that we've actually seen already many times in the last few days. The early times of the universe are where we have the most uncertainty, where we have sort of the least experimental handles. Of course, close to today, we have lots of observations that are exquisitely precise, the CMB, Big Bang nucleosynthesis. They actually set up a universe where it's very challenging, and of course that doesn't mean impossible. It's also very interesting to see what we can do and probe the limits of what we can learn, even during those epochs, precisely because they have so much data. But earlier than that, before BBM, there's really very little known. And I just wanted to sort of riff on this a little bit and maybe see if other people would like to join the discussion. And so, here's an example. If I imagine a simple freeze-out relic, so something like a WIMP, you can actually imagine that many things would go wrong with our freeze-out calculation based on our extrapolation of the universe to early times. And of course, this is all anchored by nucleosynthesis. But if we go to, if we think about a typical WIMP, it's already actually frozen out at a temperature that's much earlier, which means that the processes that set the dark matter density are actually not at all under control just by having made the observations that BBN works really well to describe the universe that we see. So for example, you could imagine that some other particle could decay into the dark matter and alter its density. You could imagine something like physics could look different from our expectations because the vacuum is actually different at that time. Maybe there's other fields that control things like couplings, etc. There are some other particles that could decay into the standard model stuff, which dilutes the dark matter that we actually produced at the time of freeze out. And there could also be an unexpected early period of matter domination or inflation. And this is a feature, right? Understanding the annihilation cross-section could verify the WIMP miracle and push back our understanding of the universe to earlier times. We've really tended to emphasize the fact that this is a constraint on theories of dark matter, but I actually think it's more interesting as a potential window to the universe. So I prepared a couple slides that talk about the idea that maybe the value of the QCD coupling could be different in the early universe such that it confines at an early time. I'm actually not even going to go through these slides. I just want to highlight what the impact is. So the idea is we as particle physicists know how to introduce dynamics that would cause the strong coupling constant to effectively take a different value. And this could lead to the strong nuclear force confining at some early epoch around, say, 100 GeV or a TeV. And then, of course, it has to go back to normal before the measurements that we're doing today. So there's a few slides here that talk about what this looks like and how you can engineer a theory like that. Basically, this field that controls the coupling's value has to have a potential that takes it from one value at high temperatures to another value at low temperatures. And we actually know more or less how to do things like that. We already see examples of them in the standard model, in fact, with the Higgs. This could actually lead to a first order QCD phase transition at early times. So you could imagine actually that unlike the QCD phase transition that we extrapolate based on what we know, there may have been an earlier QCD phase transition that was first order. And then you can do lots of fun things to calculate the properties of the universe because it's described at that point by pions and baryons. And so the pions basically become the stuff of the universe if this is happening. And the thing I really just wanted to emphasize, and I'm not going to go through the details, like I said, you could write down a theory where there's WIMP dark matter that is coupled to quarks. Then when it freezes out into pions. This can lead to a radically different cross-section for the freeze out because the cross-section for a fundamental particle to interact with pions is actually very sensitive to the scale of QCD and actually is enhanced if you enhance it. So that leads to the cross-sections being much larger. And as a result, it changes completely the prediction for the relic density such that if you just took this model and asked that it provide the correct relic density, so you fix the scale of the parameters that way, you'd find a theory that was completely excluded by xenon 1 ton already. Whereas if I raise the QCD scale to a factor of 500 or 1,000 and cause it to confine at an early time, you end up targeting a region of parameter space that is actually completely untouched by xenon. And I think that's actually a lot of fun, and it puts into perspective what it means when we do something like a relic density calculation. You can do a similar thing with the axion. Again, I don't really want to dominate the time by going through this really carefully, but the point is that the density of axions, because the axion mass is determined by the QCD scale, can also be largely affected such that you could end up with a fraction of, a density of axions compared to the one you would infer from a standard cosmology, which could be very much smaller than the one that you would have guessed. So that opens up new regions of axion parameter space. So I'm going to stop sharing here and hopefully hear some perspective from other folks.
Yeah, thanks, Tim. Do the others want to comment on this? How do they see this, the viability of what he was suggesting?
I would say, not talking specifically about changes in alpha strong, but the general approach to having windows opening up, I think, is a good point. And let me put it in the form of simplicity again, right? You know, the simplest thing that we were thinking about, say, for dark matter a long time ago, would just be, say, an extra neutrino, some third, at that time, maybe third or fourth generation heavy neutral lepton, which was stable. Of course, then you get an experiment, you know, LEP, which measures the width of the Z, and you find, no, can't be a neutrino. And then you say, okay, well, I mean, the thermal freeze out scenario, again, it's attractive because of its simplicity. You sort of erase everything that went on before, and then you just let it go, and this is what you get. You know, supersymmetry looked really good for that. And then you do the experiment and you don't discover supersymmetry at the LHC. And then you say, okay, well, it's still possible, but now the masses have to be a few TeV. And now you have to have all sorts of degeneracies in these masses. So it gets a little bit more convoluted, possible, but convoluted. So now you're starting to lose that simplicity. Well, another way to at least equally gain back some of that simplicity, say, okay, you don't have these special relationships, right? So suppose your neutralino and your stop are not nearly degenerate, and you get a thermal relic density freeze out, you know, which gives you omega of 1,000. Okay, that doesn't necessarily mean that it's all excluded, because, you know, among the list of things that Tim mentioned, you could have, you know, some entropy released into the universe, you know, well before BBN, and dilute this relic abundance, this overabundance of thermal relics. And so there are all these other possibilities. At some point, they become as simple as what you thought was simple before.
More thoughts, more comments?
Well, let's not forget pure gravity options. My favorite there is primordial black holes. I mean, there we have perfectly well-known physics, really plausible initial conditions. That's about all that goes into it. And lo and behold, you have dark matter candidates with observable consequences in the multi-messenger domain. So that's a whole new field, really, for dark matter, which I think is lots of openings, possible potential openings.
We had one comment from the audience there. Yeah, Bradley, please go ahead.
Yeah, thanks. So it sounds like we're saying that dark matter production is now an opportunity, and so we're not using, for example, freeze out as much of a guiding principle anymore. You know, freeze out is kind of used as an argument that you should be looking for something that looks like a WIMP. But you're also saying that we shouldn't necessarily be hunting for anomalies and assuming that all the anomalies might be associated with dark matter. So it now sounds like we really have no guiding principles to direct us, you know, into what theories to study or what experiments to build. So what are the guiding principles that we still have left?
I wouldn't go to
look
so
everywhere
far to say there are no guiding principles, but it is true that you know once the simplest things don't work, then you have to go to the next simplest things, and in that case there might be a large degeneracy of many next simplest things, and yeah, you don't necessarily know, you know, right now which is the way to go, and we need more information. And that's got to presumably come from experiment, unless there's a real breakthrough in theory. But Tim, you were going to say something?
No, I was just, I made the off-the-cuff answer that we should look everywhere. That's our guiding principle. Leave no stone unturned.
I think that's what I assumed at least part of the answer might be.
Okay. We have another question from the audience, Andrew.
Yeah, it's just more of a comment, I guess, and I think it dovetails with what Keith just said. And yeah, like when you think about why WIMPs were so appealing, it's not only that they were really simple, they tell a simple story of the origin of dark matter, but it's also they were like eminently testable, right? And so we have to look at the next simplest, but also most testable things and really explore those regions. I think those dual guiding principles are a good way forward, maybe.
And well motivated. There was, whether it's, you're talking about, supersymmetric candidates or axions, there was some beyond dark matter theory motivation for their existence. And well, that might still be true, right? We haven't excluded them, right? But if you go beyond that, I mean, this is obviously just personal preference and it could be completely wrong, but it would be nice if it was still somehow well motivated. If we're talking about particle dark matter, that it was still well motivated from something else in particle theory rather than just adding on more and more structure on its own just for dark matter.
I think there is one curious effect one could think about, that is to be guided by anomalies in other sectors, for example. So, we have a huge problem with understanding the cosmological constant value. So maybe there is a connection there that would, aim at some subset of dark matter theories. Another one is the black hole information paradox, which may also point us to some subset of primordial black holes. So that would be dark matter candidates. So I think that these also are clues that we should not ignore. Let's at least say that.
Okay, thanks. Maybe I can ask a question to all of you. I mean, I come more from the particle physics side, and as we all know, the LHC hasn't discovered anything, although there's still a lot of beyond what we expected from the standard model. Absolutely.
That's a big thing, though.
No, I fully agree. I phrased this completely wrongly. I fully agree with you. So we had a great discovery, but everybody was hoping for even more discoveries, and this we haven't seen. And I feel that at least in part of the community, from this part of the community, there is a bit of frustration, or they think we need something else. On the other hand, I see that from the dark matter side, we are in exactly the same situation. We've done over decades experiments and looked in all different, well, not all different corners, but many different corners, haven't seen anything. On the other hand, I see at least the four of you very optimistic and very positive, which I find very nice. I don't know whether we were just lucky to get four optimistic people here on the board, or whether there may be other reasons why you think it's easier or more imminent that we will see something, or you see the situation in dark matter and let's say normal collider phenomenology more on a similar level.
It's interesting that you think what I said was optimistic.
Well, I think,
I'm not, there's some part of optimism because I think we're pretty sure that there's dark matter in the universe. So, we've got that part settled. But what it is and its detectability, sure, there's still things to do, lots of things to do. But, imagine that, you're talking about a gravitino-like particle. Then you're not in that great of shape, right? I mean, it's a perfectly plausible dark matter candidate. You can produce it in the right abundances in the early universe. and you're not going to detect it. So, optimism is good. I mean, it keeps everything going, but there has to be some, some caution and some awareness that it might be a hard road.
Yeah, so I don't know if I would call myself optimistic.
You sounded
optimistic. Well, I don't know. I think that there are a number, at least from my perspective, there are a number of signals there. We don't know quite what to make of it. So maybe, the fact that there is something there that could be potentially dark matter, maybe keeps some of us optimistic. The problem is that there is a lot of hard work to do to actually sort it out. So, okay, well, we got to do it if nothing else comes up. One thing that keeps me maybe excited about this whole dark matter hunt is new and upcoming experiments. And in this case, I'm talking about Ruby and LSST using these, astrophysical probes to learn more precisely how dark matter is distributed, like using gravitational lensing to probe dark matter, the dark matter substructure mass function. And those are all observations that potentially can tell you a lot about the nature of dark matter. Also, for instance, looking at stellar streams to see how much they've been disrupted by substructure, and using that kind of observation with future survey to give us some more insight of what the dark matter could be. So I think I'm hopeful. But there are things in the near future that, and a lot of hard work that comes with it, that hopefully will give us an answer in the next maybe 10 years. I don't know. Let's fingers crossed.
More comments on this? I mean, maybe you are in a good, or we are in a good position because there are actually several experiments in the future approved. Yeah, that will tell us something more. Whereas in collider physics, we are struggling to get something beyond the LHC. So maybe this also contributes to optimism on one and less optimism on the other side. The experiments are still cheaper. If you don't see anything, then they will get more and more expensive, and you will get into the same situation probably.
That might be a nice way to look at it, Sven. It's not so much optimism as it is opportunity. When there is lots of opportunity, right, then there is a lot of reason, there's a lot to do. And, we're all doing this because we like doing it as well as the actual getting the answers.
Yes, yes.
There's another interesting issue, which is to do with budgets, actually. As our experiments, some of them get more and more expensive, such as the future, perhaps 100 TV collider, you have to wonder whether you...
Oops.
You froze.
Yes. Let's wait until he comes back and then he can repeat maybe.
Yeah, for some of us, the 100 TV collider is a little bit like metaphysics because it won't exist in our future.
In our future, yes.
In our future.
In our grandchildren's future, maybe.
Yeah. Yes. So when you were starting to speak, your connection broke up, so we don't know what you wanted to tell us.
Yeah,
sorry.
The last thing we heard was 100 TV collider, Joe.
Yes.
Yeah, I was just saying that there are huge budgetary issues that have to be folded into all of this. So you have to ask the question, would you be better off, for example, having a lot of small experiments aimed at different aspects of dark matter technology, or...
Oops.
Now we can try to imagine. Yeah.
I think I don't know if Joe can hear or not, but it depends on what your goal is, right? 100, I think it would be a hard case to make to build a 100 TV collider only to discover dark matter. What you're really looking for is some extension of the standard model, some physics, some new physics beyond the standard model, which, we suspect should be there, but whether it's, below 100 TV or not, we don't know. And the only way to find out is to build the machine. But yeah, I mean, nobody's talked really about CMB, or at least in the last hour or so, nobody's talked about CMB, but there's going to be more progress there. And that will come, and that will come, I think sooner on some of these timescales rather than later. And we're waiting for that tensor to scalar ratio, for example, and hopefully we'll learn more as well from CMBS4.
Yeah. Okay. Any other final remark, either from the audience to you or from you to the audience? Well, as I said, I at least perceive the four of you as optimistic, which brings me in a good mood. I was very happy about this. Then maybe with this still optimistic note, we can conclude the workshop. We had 4 interesting days based on different topics, and many experts could talk about either an overview or their latest results. Overall, very interesting. Thanks a lot to all of you who contributed. And I don't know whether Bradley, who was kind of our main organizer, wants to say something more.
Thanks, Sven. I'll just say the same. Thanks everybody who contributed, everyone who helped organize, and the audience for coming along and taking part. I think it's been really interesting. And I think obviously we couldn't have done it without everybody being involved. So thanks a lot. And
of course, we hope that in 1 year or 2 years latest, we will meet in 3D again.
Yeah, come back, see us in person.
I am very optimistic.
And special thanks to Bradley. As Ben mentioned, he has definitely taken the lead on organizing this conference.
Yes. I have to join that congratulations to Bradley.
Okay.
It was a pleasure. Thank you, everyone.
Then, see you hopefully soon again in person, and all the best to all of you. Yeah. Okay. Bye bye.
Thanks everyone.
Thanks everybody. Bye.
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 Thank you.
Bye.
Bye bye.
Bye bye.